Every noodle, pasta shape, and cheesy curl begins as a simple blend of flour and water. Inside the factory, powerful mixers, steam dryers, and precision cutters turn dough into thousands of perfect pieces ready for cooking. Today, we uncover how noodles, pasta, and mac and cheese are made, from raw grains to the golden, comforting dishes we love. Wheat flour is first delivered into large stainless steel silos, where it is aerated and sifted to remove any foreign particles. From the silos, the flour is conveyed pneumatically into a mixing chamber. Inside the mixer, filtered water and a carefully measured dose of alkaline salts, typically potassium carbonate and sodium carbonate, are added. These alkaline agents raise the pH of the dough and produce the distinctive yellow color and firm, springy texture characteristic of cup noodles. The mixing chamber is equipped with twin shafts fitted with spiral paddles. These rotate in opposite directions, kneading the flour and water into a coarse dough. After a preset mixing time, the dough exits through a discharge chute and drops onto a sheeting conveyor. A pair of compression rollers press the dough into a wide, flat sheet of uniform thickness. The dough sheet then moves through a series of calibrated rolling stations. Each set of rollers reduces the thickness incrementally. Final gauge rollers press the sheet to a precise thickness, usually around 1 mm, before it enters the slitting unit. Here, rotary cutting wheels slice the sheet into long continuous strands. The blades rotate in exact synchrony with the moving dough, ensuring even noodle width and preventing tearing or overlap. The cut strands are separated by a vibrating spreader and immediately fed into a wave former. This mechanism applies a rhythmic up and down motion as the noodles pass over metal rods. The result is the iconic wavy noodle shape. The wave pattern is fixed into the strands by partially steaming them immediately after shaping. The noodles then enter a vertical steam chamber. Superheated steam, delivered through multiple nozzles, cooks the noodles for a brief but precise interval. The starches gelatinize and the surface becomes slightly sticky. This step fixes the texture while keeping the strands pliable. Upon exiting the steam chamber, the noodles are portioned. A wire cutter slices the strands into fixed lengths, which are gathered into bundles by rotary collectors. Each bundle is compressed slightly to form a compact cake. These cakes are positioned over pre-formed polystyrene foam cups on a conveyor system. Using a synchronized pick-and-place system, the noodle cakes are inserted into the cups from above. The cups themselves are formed earlier in the process using vacuum thermoforming machines. Polystyrene sheets are heated and drawn into mold cavities using vacuum suction. After forming, the cups are trimmed, stacked, and fed automatically to the noodle filling station. Once the noodle cake is placed into the cup, it proceeds to the dehydration stage. Unlike many instant noodles that are fried flat, cup noodles use a unique upside-down flash frying method. The filled cups are inverted and loaded onto a wire mesh conveyor belt that carries them through a continuous oil fryer. The oil, typically palm oil or a blend of vegetable oils, is maintained at a stable high temperature, usually between 140 degrees Celsius and 160 degrees Celsius. As the cups travel upside down through the fryer, the noodles are rapidly fried. Moisture evaporates from the strands, creating a porous, dehydrated structure that can be rehydrated quickly with hot water. The upside-down orientation ensures that the noodle cake maintains its shape and settles evenly inside the cup. Frying time is tightly controlled to prevent overcooking or excessive oil absorption. After frying, the cups exit the oil bath and are conveyed through an inclined cooling tunnel. High-speed fans blow filtered ambient air over the hot cups to bring them to a stable handling temperature. Sensors monitor the internal temperature of the noodles to ensure uniform cooling before the next stage. Flavoring ingredients are added next. A separate filling system dispenses dried soup base and dehydrated vegetables or meats into each cup. The powder and inclusions, such as corn, peas, green onion, shrimp, or meat bits, are pre-blended in large hoppers. These are vibrated to prevent clumping and ensure free flow. As each cup passes underneath a dosing unit, precise quantities of the flavor mix and inclusions are released. Auger fillers handle the powder, while rotary cups or belt feeders portion the solid pieces. Lidding is the next step. A continuous roll of pre-printed aluminum foil is fed through a cutting die and sealing station. The foil is heat sealed onto the lip of each cup using a combination of pressure and temperature. The seal must be strong enough to prevent contamination, but easy to peel by hand. A vacuum system removes any air trapped between the noodle surface and the foil lid prior to sealing, reducing oxygen exposure and extending shelf life. Lidded cups proceed to the shrink sleeve labeling unit. A plastic film sleeve is positioned over each cup and then passed through a steam tunnel. The heat causes the sleeve to contract tightly around the cup, conforming to its shape. This sleeve contains branding, nutritional information, and preparation instructions. The orientation is adjusted using optical sensors to ensure perfect alignment with the cup's front face. After labeling, the cups are inkjet coated with production data, including date codes and batch numbers. A vision inspection system verifies code legibility and checks for misaligned labels or incomplete seals. Any defective cups are rejected automatically onto a side conveyor for rework or disposal. The finished, sealed, and labeled cups then enter the secondary packaging area. Depending on the distribution format, cups are grouped into packs of 6, 12, or 24 using a mechanical collator. These are pushed into pre-erected cardboard cartons supplied by a case-forming machine. Hot melt adhesive is applied to the flaps using spray nozzles, and the boxes are pressed shut by compression rollers. Each sealed carton passes over a check weigher to confirm correct content mass. Barcodes and product identifiers are applied using print and apply labeling machines. Cameras scan the labels to verify print quality and correct placement. The cartons are then transferred to the palletizing station. Robotic palletizers equipped with vacuum grippers or pneumatic pads stack the boxes onto wooden pallets in alternating layer patterns. Each layer is indexed and leveled using precision edge guides. Once a pallet reaches its designated height, it moves to the stretch wrapping station. Here, plastic film is wrapped around the pallet while it rotates on a turntable. Tension control and overlap percentage are adjusted dynamically based on pallet shape and weight. The wrapped pallets are labeled with a logistics ID and transferred by automated guided vehicles or forklift to shipping docks or warehouse storage zones. In parallel, all ingredients used in cup noodles, flour, salts, oils, seasonings, and dried vegetables are stored in bulk tanks and silos. These are monitored continuously for level, humidity, and temperature. Flour is conveyed pneumatically from storage to mixers. Water for the dough is filtered and UV sterilized before use. Oil for frying is circulated through a closed-loop filtration system that removes particulates and maintains clarity. Spent oil is drained and replaced after a set number of frying cycles, tracked by production batch logs. Quality control checkpoints exist at every stage. During dough mixing, operators monitor water absorption and dough elasticity using resistance sensors and torque readings. Sheet thickness is verified with laser micrometers before slitting. The width and wave depth of the cut noodles are measured optically in real time. Caramelization level and texture of the fried noodles are sampled from each batch and tested for rehydration time and oil content. Soup base and seasoning powders are blended in large ribbon mixers fitted with load cells and sampling ports. Moisture levels in dried inclusions are measured by infrared sensors before dosing. Sealing strength of foil lids is tested by applying standardized pressure until rupture. Seal failures beyond tolerance trigger immediate alarms. The entire production process is managed through a distributed control system, DCS. Each major component, mixers, fryers, fillers, lid sealers, labelers, is equipped with a PLC. These units communicate with a central control interface where operators can monitor flow rates, dough temperature, oil usage, fill weights, and output speed. Recipes and production profiles are saved digitally, allowing fast switchover between flavor variants or cup sizes. Sanitation is performed on a rotating schedule. Between shifts or recipe changes, dough mixers and noodle rollers are cleaned with high-pressure water and food-safe detergents. Fryers are drained and flushed with flushing agents. Dosing systems for powders and inclusions are disassembled and brushed manually. Cup molds and conveyors are wiped down using alcohol-based surface cleaners. Durum wheat semolina is the primary raw material used in pasta manufacturing. It arrives in bulk and is unloaded into stainless steel silos equipped with aerators and sifters. These silos store the semolina under controlled temperature and humidity. From the silos, semolina is conveyed pneumatically into a weigh hopper, where precise quantities are measured before entering the mixing system. Water is added to the semolina through a dosing pump as both ingredients enter the horizontal pre-mixer. The water is filtered and temperature controlled to ensure consistent dough development. The pre-mixer is a twin-shaft system with overlapping paddles that combine the semolina and water into a crumbly, granular dough. This stage typically lasts for 10 to 15 minutes, and no gluten is developed here, only hydration. The hydrated mixture then flows into a vacuum kneading chamber. This vessel contains a large screw auger that compresses and kneads the dough under vacuum. Air is evacuated to eliminate oxidation and reduce bubbles in the final product. Under pressure, the dough begins to form a cohesive, elastic mass. The kneading screw pushes the dough forward into the pasta press. The pasta press consists of a compression screw housed in a barrel. As the screw rotates, it applies mechanical pressure, forcing the dough forward toward the die head. Just before extrusion, the dough passes through a second vacuum chamber that removes residual air. This double vacuum system ensures smooth surface texture and prevents breakage during drying. The die head holds a brass or Teflon-coated die plate with dozens of holes shaped according to the type of pasta being produced: spaghetti, penne, fusilli, farfalle, or others. As the dough is pushed through the die, it takes on the corresponding shape. For shortcut pasta, like penne or rigatoni, a rotating blade mounted just beneath the die slices the extruded strands at uniform lengths. Blade speed and position are adjustable to control piece size. Immediately after cutting, the pasta falls onto a vibrating belt that separates and aligns the pieces. The belt feeds into a pre-dryer, a short chamber with warm air at low humidity. Here, the surface moisture is reduced to prevent sticking and deformation during handling. This stage lasts only a few minutes, but it's crucial for shape retention. For long-cut pasta, like spaghetti or fettuccine, strands are laid continuously onto rods or loops by an automated looping device. These rods are transported by conveyor into multi-stage dryers. The entire drying process is tightly regulated. Primary drying begins in a chamber where temperature and relative humidity are gradually increased. Warm air, typically between 55 degrees Celsius and 75 degrees Celsius, circulates through the pasta via fans and ducting systems. The airflow direction alternates to ensure even drying. Sensors monitor surface moisture content, and the pasta's structure begins to stabilize. In the next phase, stabilization, the temperature is held steady while humidity is slowly reduced. This allows the interior of the pasta to release moisture at the same rate the surface loses it, preventing cracks and internal stress. Each dry zone has PID controllers that adjust heat and airflow in response to real-time sensor feedback. The final phase, cooling, brings the pasta down to ambient temperature using filtered, dehumidified air. For long pasta, the hanging rods pass through these zones slowly over 6 to 10 hours. Shortcut pasta is dried on vibrating trays or mesh belts in large cabinet dryers that rotate trays periodically for even exposure. After drying, long pasta is automatically lifted from the rods and cut to standard retail lengths, usually 25 centimeters. The cut strands fall gently onto conveyor belts equipped with brushes that remove excess flour and broken tips. The pasta is then transferred to a vibrating sifter that separates any fines or small fragments. Short pasta, once dried and cooled, is conveyed into a series of screens and classifiers. Pieces outside the tolerance range, too short, broken, or malformed, are diverted to rework bins. Accepted product moves on to weighing and packaging. For packaging, pasta is first collected into hoppers above a multi-head weigher. These weighers use load cells and sensors to release exact quantities, 250 g, 500 g, or 1 kilogram, into form, fill seal machines. Plastic film from large rolls is drawn into a forming collar and sealed around the falling pasta. Vertical sealing bars close the side, while horizontal sealing jaws crimp and cut the top and bottom. During sealing, vacuum nozzles or nitrogen flushing may be used to displace ambient air, extending shelf life. As each bag is formed and sealed, it passes beneath an inkjet printer that applies batch codes and expiration dates. Optical readers verify that print is clear and correctly positioned. For pasta sold in boxes, a different system is used. A volumetric filler dispenses pasta into an open-top carton traveling on a belt. Flaps are folded and glued by rotating arms, and the filled cartons pass through compression belts to ensure a tight seal. All packages, regardless of format, are collected into groups using collators. They are placed into corrugated cases by robotic case packers. Each case is built automatically from flat blanks sealed with hot melt glue and labeled using a print and apply labeler. Barcode scanners verify case content before palletizing. At the palletizing station, articulated robotic arms use vacuum grippers to pick and stack cases onto wooden pallets. Patterns are adjusted depending on case size and weight. Slip sheets may be inserted between layers for added stability. Once a pallet reaches full height, it is wrapped in stretch film using a turntable or robotic arm wrapper. The wrapped pallets are labeled and scanned into the warehouse inventory system. Forklifts or automated guided vehicles, AGVs, move the pallets to staging areas for outbound shipping. Throughout the process, quality control systems operate continuously. Semolina is analyzed for protein content, granule size, and moisture before use. Dough hydration is monitored using inline sensors that measure torque and consistency during mixing. Pasta diameter, wall thickness, and length are checked by laser micrometers at multiple stages. Moisture content in finished pasta is tested using infrared drying units or moisture balancers. Samples are also tested for cooking time, firmness, and swelling index. If any deviation occurs, the batch is flagged and removed from production. Clean in place, CIP, systems clean the dough mixers, extruders, and piping between production runs. Dry areas, like dryers and sifters, are cleaned manually using compressed air, brushes, and vacuum systems. Hygiene protocols are rigid to prevent contamination between product types. Die plates are removed and cleaned with pressurized water and ultrasonic tanks. Every die is catalogued and rotated based on shape and wear rate. Teflon-coated dies produce smoother pasta surfaces, while bronze dies give a rougher texture preferred for sauce adhesion. Air used in drying and cooling is filtered and conditioned. HEPA filters remove particulates, while dehumidifiers ensure consistent airflow. Each dry zone is mapped for temperature and humidity uniformity, using multiple sensors connected to a centralized control system. The entire production line is governed by a SCADA, supervisory control and data acquisition system. Operators monitor flow, pressure, motor speed, and temperature in real time from touchscreen panels. Recipes for each pasta shape are stored digitally and recalled instantly during changeovers. Mechanical actuators adjust die plates, blade positions, and packaging formats based on the selected recipe. Ingredient handling is fully automated. Semolina flows from silos through sealed conveyors. Water is filtered, dosed, and monitored with UV sterilizers and flow meters. Lubricants used in machines are food grade and monitored to prevent cross-contamination. Production runs are planned in batches, but the process is continuous. Pasta moves through mixing, extrusion, drying, and packaging without interruption. Only during scheduled maintenance or product changeovers does the line stop. From flour to fork, pasta manufacturing is a highly engineered sequence of mechanical, thermal, and pneumatic operations. Dough becomes structured through pressure and hydration. Shapes are formed under vacuum and cut by precision blades. Moisture is drawn out gradually in chambers humming with air currents. Machines fill, seal, stack, and wrap, synchronized by sensors and driven by control logic. Macaroni and cheese manufacturing begins with the continuous production of elbow macaroni, the signature pasta shape. Durum wheat semolina is stored in sealed silos where it's kept under controlled humidity and aeration. The semolina is pneumatically conveyed to a whey hopper, then released into a high-speed horizontal pre-mixer. As the mixer runs, filtered water is injected in precise amounts through a flow-controlled nozzle system. The mixture forms a coarse, granular dough with no gluten development at this stage. The moistened dough transfers to a vacuum kneading chamber. Here, a slow-turning screw applies pressure to compress the particles into a cohesive mass. A vacuum pump removes excess air, preventing oxidation and ensuring the pasta will have a smooth surface and uniform color. The dough advances through a compression auger toward the pasta press. At the end of the press, the dough passes through a forming die. For elbow macaroni, the die includes a curved extrusion channel that forces the dough into a bent tubular shape. As the pasta is pushed through, a rotating knife cuts the curved tubes at uniform intervals. Blade speed is adjusted in coordination with dough pressure to maintain consistent piece length, typically around 2.5 to 3 centimeters. Freshly extruded macaroni is fragile and contains residual moisture. It is transferred by vibrating conveyor into a pre-dryer. This chamber uses warm, low-humidity air to gently reduce the surface moisture and fix the shape. This step lasts 1 to 3 minutes and stabilizes the pasta for handling. The pre-dried pasta moves to a vibrating spreader that distributes it across a mesh belt, feeding into a multi-zone drying chamber. Inside the dryer, temperature, humidity, and airflow are carefully regulated. The first zone heats the pasta to 65-80 degrees Celsius, beginning internal moisture reduction. Airflow alternates above and below the mesh to dry evenly. In the middle zones, humidity is decreased gradually while heat is maintained. This balance prevents surface hardening or internal cracking. The final zone is a cooling section. Here, filtered ambient air lowers the temperature of the pasta to prevent condensation and to prepare it for packaging. Total drying time ranges from 4 to 8 hours, depending on pasta diameter, density, and production volume. The dried macaroni is discharged onto vibrating sieves that remove any undersized or broken pieces. Acceptable product moves by conveyor to a vertical bucket elevator, lifting it into a hopper above the packaging line. From here, pasta is fed into multi-head weighers that release fixed quantities, typically 200g to 400g, into individual pouches. While pasta is being processed, cheese powder mix is prepared in a separate blending operation. Ingredients including dehydrated cheese, whey, milk solids, salt, sodium phosphate, citric acid, and annatto are dosed from stainless steel silos and hoppers into a ribbon blender. The blender combines the powders using overlapping blades that tumble the mix in opposite directions. Uniformity is critical. Each pouch must contain identical flavor and solubility properties. After blending, the cheese powder is sifted through a vibratory screen to remove agglomerates. It is then conveyed to a secondary packaging station. A separate form-fill-seal machine doses a measured amount of cheese powder, typically 20g to 30g, into heat-sealed pouches made from laminated film with oxygen barrier properties. Each pouch is coded with batch and expiration data and conveyed for integration with the pasta. In the combination stage, one pasta pouch and one cheese powder pouch are merged. Collation conveyors synchronize both lines, bringing pasta and cheese pouches together just before cartoning. A horizontal cartoning machine erects cartons from flat blanks, folds the bottom flaps, and holds them open with mechanical fingers. A robotic arm inserts the combined pouches into each open carton. Once filled, the top flaps are closed and sealed using hot melt glue. As cartons exit the sealing station, inkjet printers apply product codes, date stamps, and barcodes. Cameras verify code presence and alignment. Rejected cartons are automatically diverted to a separate line for inspection or rework. Correct cartons proceed to case packing. Cartons are grouped using an inline collator and pushed into a corrugated case supplied by an automatic case erector. Hot glue or tape is applied and the flaps are sealed. Each case passes through a check weigher to verify total contents and is labeled with a print and apply system. The label includes product ID, case count, and tracking data. At the palletizing station, robotic arms stack sealed cases onto wooden pallets. Vacuum pads, or gripper arms, lift and rotate boxes into aligned layers. Slip sheets are inserted automatically every few layers for added stability. Completed pallets move to a stretch wrapping turntable, where film is wrapped around the load under controlled tension. While packaging is underway, the dry blend operation also prepares bulk cheese powder for institutional or bulk formats. In this variation, cheese mix is loaded into large gusseted bags or drums. Powder filling machines operate under HEPA-filtered enclosures to control dust. Filled bags are sealed with continuous band sealers and printed with lot codes before being packed into master cases. Raw materials for both pasta and cheese powder are delivered in bulk and undergo stringent intake controls. Semolina is tested for protein content, ash level, and granulation. Cheese powder inputs are sampled for moisture, pH, and flavor profile. Silo inventory levels are managed using load cells and level sensors. Water for dough mixing is filtered, UV treated, and temperature controlled. Air used in dryers and conveyors is HEPA filtered and dehumidified. Oil lubricated machinery in contact with product zones uses food-grade lubricants only. All processing equipment is stainless steel, with sloped surfaces and minimal joints to aid cleaning. Production lines are monitored through a central PLC-based control system. Operators use touchscreens to set parameters for extrusion pressure, knife speed, dry temperatures, fill weights, and glue patterns. All parameters are saved in production recipes, enabling rapid line changeovers for different pack sizes or formulations. Extruder head pressure, dough torque, and vacuum levels are logged continuously. Dryer systems include multiple thermocouples and humidity sensors managed by PID loops for responsive control. Air velocity through the drying chamber is measured and adjusted automatically to prevent temperature layering or hot spots. Clean-in-place systems are used to sanitize closed-loop components such as pasta augers, cheese, mix lines, and filler hoppers. Open surfaces are cleaned during scheduled downtime with pressurized water and food-safe detergents. Verification is conducted using swab tests and ATP monitors. Quality control is integrated throughout the line. Pasta is inspected for length, curl radius, color, and residual moisture. Laser micrometers measure wall thickness and internal diameter. Finished pasta is tested for cooking yield, firmness, and disintegration resistance. Cheese powder is evaluated for blend consistency, flavor, and solubility. Random packs are rehydrated and cooked to simulate consumer preparation. Packaging integrity tests include burst tests, seal strength, and vacuum retention for pouches. Cartons undergo drop testing and compression tests to ensure they withstand transit conditions. For single-serve or microwavable mac and cheese, the process begins similarly with pasta production. However, instead of dry packaging, cooked pasta is used. The pasta is first boiled in industrial cookers, long troughs with recirculating hot water systems. After cooking, pasta is cooled rapidly in rotary chillers with cold water spray and air blowers. Cooked pasta is dosed directly into plastic microwavable cups or trays using multi-head filling machines. Cheese sauce, prepared in heated kettles, is pumped into a separate filling head. The sauce is hot-filled immediately after preparation, using servo-controlled pistons that regulate volume and flow rate. After filling, the trays or cups are sealed with foil lids using heated platen sealers. Lidded units are passed through a tunnel pasteurizer, where steam or hot water raises the internal temperature to sterilize the contents. After pasteurization, the products pass through a cooling tunnel with chilled air to bring them to ambient temperature for packaging. Microwavable cups are labeled with shrink sleeves or wraparound labels. Each unit is inspected for fill level, lid seal, and label alignment. These are packed into display cartons, cased, palletized, and shipped with the same downstream systems as dry pack boxes. From raw wheat and powdered cheese to complete boxed or ready-to-eat products, mac and cheese production is a tightly orchestrated process of extrusion, drying, blending, dosing, and packaging. Each component, elbow macaroni and cheese powder, follows a distinct line until their paths converge. Machines extrude thousands of macaroni tubes per minute, slice them, dry them, and screen them into uniform shapes. Ribbon blenders tumble cheese powder until it's perfectly homogeneous. Pouches are filled, sealed, combined, and boxed with mechanical precision. The process for Reese's peanut butter cups begins with the sourcing of high-quality raw peanuts, which form the core of the filling. These peanuts are typically sourced from farms in the southeastern United States, particularly Georgia, Alabama, and the Carolinas, where the climate and soil are ideal for peanut cultivation. Once harvested, the peanuts undergo initial cleaning, shelling, and sorting at the agricultural level before being shipped in bulk to the Reese's production facility. Quality control teams inspect every shipment, screening for mold, aflatoxins, and other contaminants. Peanuts are often tested for size, moisture content, and oil composition to ensure batch consistency. Upon arrival at the factory, the peanuts are conveyed to large storage silos. From here, the process of transforming raw peanuts into the signature Reese's filling begins. The peanuts are first roasted in large-scale industrial roasters, long horizontal drums heated by indirect gas-fired flames. These rotating drums tumble the peanuts slowly, ensuring even roasting. Temperature and humidity are closely monitored throughout the roast cycle, typically maintained around 320 degrees Celsius for about 30 to 40 minutes, depending on the peanut variety and moisture content. Once roasted, the peanuts are quickly cooled using forced air cooling tunnels to halt further cooking. The skins are then removed using a process known as blanching. In mechanical blanches, peanuts are agitated against rough surfaces or rubber belts that strip away the thin, papery skins. A series of air jets and vibrating sieves separate the skins from the now blanched nuts. At this point, the peanuts are ready to be ground. In most candy factories, this process takes place in two distinct phases. First, a coarse grind reduces the peanuts into a crumbly paste. Then, a finer grinding process, often using high-speed colloid mills or stone rollers, produces a smoother texture. However, unlike creamy commercial peanut butters designed for spreads, Reese's peanut butter filling maintains a slightly gritty texture on purpose. This signature mouthfeel is the result of limiting the duration of the fine grind and carefully controlling moisture levels. The ground peanuts are blended with additional ingredients, including sugar, dextrose, salt, hydrogenated vegetable oils, and sometimes a small amount of molasses or corn syrup solids. This mixture is prepared in large industrial mixing tanks equipped with powerful paddle agitators that ensure even incorporation. The blending process is closely monitored for temperature, viscosity, and particle size distribution, which directly affect the final texture and handling characteristics. The resulting peanut butter filling is slightly crumbly, yet cohesive, designed to hold its shape when formed, but melt smoothly in the mouth. While the peanut butter filling is being prepared, another part of the factory is busy tempering chocolate. Reese's peanut butter cups use a custom milk chocolate formulation that includes cocoa solids, cocoa butter, milk fat, sugar, lecithin, and vanillin. These ingredients are pre-blended and then passed through conching machines, large vats where granite rollers continuously knead the chocolate for hours at elevated temperatures. Conching improves texture and flavor by breaking down particles and promoting the development of complex chocolate notes. After conching, the chocolate is sent to tempering units, which precisely heat and cool the chocolate in a controlled sequence to encourage the formation of stable cocoa butter crystals. Proper tempering is critical to achieving that characteristic Reese's snap and glossy finish. The chocolate must be maintained at a working temperature of approximately 88 degrees to 90 degrees for milk chocolate, depending on the formulation. Now the production line shifts into high gear with the molding and filling of each peanut butter cup. The factory floor features a long assembly line comprising conveyor belts, servo-driven depositing heads, forming stations, and robotic arms, all synchronized with computer-controlled systems. First, paper cup liners are dispensed from reels and dropped into aluminum or plastic molds that give the peanut butter cup its distinctive ridged edge. These molds are carried forward on the conveyor to the chocolate depositing station. Here, a metered amount of tempered chocolate is deposited into each mold cavity, typically via piston-driven depositors with highly accurate flow control. The molds are then gently vibrated to level the chocolate and remove any trapped air bubbles. A specialized spinning or centrifugal molding mechanism is often used to coat the sides of each liner with chocolate, forming a thin shell that will encase the peanut butter filling. Once the bottom and sides of the shell are set, often using brief passes through cooling tunnels chilled to 40° F, the molds move to the filling station. At this point, the peanut butter mixture is slightly warmed to improve flowability and deposited into the center of the chocolate shell using a second set of depositors. The volume and placement are tightly controlled to ensure the filling does not breach the shell's perimeter, which would compromise product appearance and shelf life. The partially filled molds then travel through another cooling tunnel to partially firm up the filling before the final chocolate cap is added. At the next station, another measured deposit of tempered chocolate is layered on top to fully enclose the peanut butter. Vibratory and centrifugal actions again ensure that the top layer is smooth and fully seals the filling inside. After the top layer is applied, the molds pass through the final cooling tunnel. This tunnel, often more than 30 feet long, gradually lowers the product temperature to about 50 degrees to 60 degrees F, allowing the chocolate to fully crystallize and harden without cracking or bloom. At the end of the tunnel, robotic demolders invert the trays and the solidified Reese's peanut butter cups drop gently onto another conveyor belt, which carries them to the packaging line. Packaging is a critical part of the operation, both for aesthetics and product protection. Individual cups are wrapped in printed foil or plastic film using high-speed flow wrapping machines. These machines align, wrap, heat seal, and cut the packaging material in a continuous motion at speeds of hundreds of units per minute. Sensors and vision systems verify proper alignment, seal integrity, and date coding. Multiple wrapped cups are then grouped into standard pack formats, such as 2-packs, king size, or multi-packs, using pick-and-place robots that transfer the wrapped candies into cardboard sleeves or blister packs. These are then loaded into shipping cartons by automated case packers and sent through weight check stations and metal detectors for final safety assurance. Cartons are sealed, barcoded, and palletized using robotic palletizers that arrange the boxes into stable stacks ready for shipment. The finished pallets are shrink-wrapped for transport and loaded onto refrigerated trucks, if necessary, depending on the season and destination. Distribution centers receive the pallets and coordinate the movement of Reese's products to retail chains, vending machine operators, and wholesale clubs. Shelf life is generally around 6 to 9 months, and climate-controlled storage is crucial to preventing fat bloom or flavor degradation in the chocolate. Inventory is rotated using first-in, first-out logistics to ensure product freshness. Reese's peanut butter cups may seem like a simple treat, but their production involves a complex interplay of food science, automation, engineering, and quality control. Each cup reflects countless micro-adjustments made by operators, engineers, and sensors throughout the line to maintain consistency in taste, texture, and visual appeal. Whether you're biting into a miniature, a king size, or a seasonal shape, the same rigorous standards apply across every variation. The process for Snickers begins long before a single bar is formed. It starts with the procurement of raw ingredients, each of which must meet stringent quality, flavor, and food safety standards. The peanuts used in Snickers are typically sourced from large-scale growers in the United States, particularly Georgia, Texas, and Alabama, where soil composition and climate are well suited to peanut cultivation. Once harvested, the peanuts undergo shelling, drying, and initial quality control before arriving at the candy factory in bulk loads. At the receiving dock, they're sampled and inspected for size uniformity, absence of mold or aflatoxins, and overall freshness. The peanuts are then conveyed to roasting units, large, gas-fired, rotary drum roasters that tumble and cook the nuts evenly. Roasting time and temperature are carefully controlled, often in the range of 300 degrees to 330 degrees, to ensure the development of the characteristic deep nutty flavor and golden color. As the peanuts cool on vibratory trays with forced air, their skins are loosened and removed through mechanical blanching, which typically involves abrasion and suction systems. Once the peanuts are blanched, they are screened again for foreign matter or off-grade pieces before being held in stainless steel hoppers, ready for integration into the bar. While the peanuts are being prepared, another production stream begins with the making of the nougat layer, the foundational component of every Snickers bar. Nougat is a whipped mixture, typically composed of sugar, corn syrup, egg whites, and milk powder. The sugar and corn syrup are first combined in massive stainless steel cooking kettles, where they are heated to a precise temperature, usually around 240 degF to 250 degF, to achieve the correct sugar structure and viscosity. This hot syrup is then transferred to continuous mixing tanks, where it is combined with whipped egg whites and other dry ingredients. The blending process is highly aerated, giving the nougat its light, spongy texture. The finished nougat is deposited onto a moving conveyor belt lined with parchment or plastic film. It spreads out in a continuous sheet, generally about 1 to 2 inches thick. A series of levelers and rollers ensures uniform height and density across the sheet, which is then cooled slightly as it travels down the line. Once cooled and set, the nougat sheet proceeds to the caramel layering station. Caramel production occurs in its own dedicated section of the plant. A blend of glucose syrup, sucrose, dairy cream, and butter is cooked in open-jacketed kettles or vacuum cookers, where it is continuously stirred to avoid burning and to control the Maillard browning reactions that give caramel its signature flavor. The exact temperature and cooking duration are tightly monitored, typically between 240 degrees Celsius and 260 degrees. As soon as the desired consistency is achieved, firm enough to hold its shape but pliable enough to slice, it is poured or extruded onto the moving nougat sheet. The hot caramel forms a second, cohesive layer atop the nougat. To ensure perfect adhesion and uniform thickness, the bar sheet passes under heated rollers and through spreading nozzles that guide and adjust the caramel's distribution. The line is equipped with infrared sensors and weight check systems that continually monitor thickness and material ratios. Once the caramel has slightly cooled and stabilized, the bar sheet moves toward the peanut application zone. Roasted peanuts are sprinkled onto the warm caramel layer in a controlled shower using vibrating feed trays and metered dispensers. The combination of slightly sticky caramel and downward pressure ensures that most peanuts adhere securely. Excess or misaligned nuts are brushed away by rotating silicone paddles and collected for reuse or reprocessing. The peanuts used here are not only flavor critical, but also provide a distinctive crunch and texture contrast to the softer nougat and caramel. With all three internal layers assembled, nougat, caramel, and peanuts, the composite sheet now travels to the cutting area. Here, guillotine-style knives or rotary blade systems cut the long sheet into bar-length strips, typically around 1 inch wide. These strips are then cross-cut into individual bars, using synchronized high-speed blades. Every bar is now a complete unit, except for the chocolate coating. Before coating, the uncoated bars, often referred to as centers, pass through a quick chilling tunnel to firm up the layers and maintain bar integrity during enrobing. Once firm, the centers are deposited onto a wide enrobing belt that passes through a chocolate waterfall. This enrobing process involves a curtain of tempered milk chocolate cascading down over the moving bars. As the bars move through the curtain, chocolate coats the top and sides. A bottoming plate or chocolate pool beneath the bars coats the underside as well. The chocolate used in Snickers bars is a proprietary blend of milk chocolate ingredients, cocoa butter, cocoa liquor, sugar, milk solids, and emulsifiers. The chocolate is pre-tempered in dedicated machines that heat and cool it through specific curves to ensure stable crystal formation. This tempering is what gives Snickers its glossy finish and prevents fat bloom during storage. The temperature of the chocolate is carefully maintained between 86 degrees Celsius and 90 degrees Celsius throughout the enrobing line. As the chocolate-coated bars exit the enrober, they pass under air jets and vibrating rods known as air knives and vibrators that remove excess chocolate, improve coating uniformity, and give each bar its final shape. The still warm chocolate is soft and easily deformed, so the bars immediately enter a cooling tunnel, which gradually reduces their temperature to around 50 degrees Celsius in a staged fashion. This gradual cooling prevents cracking and ensures that the chocolate shell sets with the correct texture. Once fully cooled, the bars emerge, ready for wrapping. A high-speed automated packaging line awaits, where each bar is individually wrapped using roll-fed film wrappers. These machines synchronize bar movement with film feeding, folding, sealing, and cutting, all in one continuous operation. Heat sealers close the film edges with precision, while inline printers apply best buy dates, lot numbers, and traceability codes. The wrapped bars are then conveyed to a grouping station. Depending on the market, Snickers bars may be packed individually, bundled in twin packs, or combined into multi-unit boxes. Robotic arms sort and orient the wrapped bars, placing them into cartons that are then sealed with hot melt adhesive. The packed cartons are passed through metal detectors and weight verifiers as a final check before palletization. Palletizing robots load the boxes onto standardized pallets, wrapping them tightly in plastic film for protection and stability during shipping. From there, pallets are staged in climate-controlled distribution centers. Temperature and humidity must be carefully controlled, especially in warm climates, to preserve the bar's texture and chocolate integrity. Snickers bars are then distributed to retailers, wholesalers, and vending machine operators worldwide. Shelf life for a standard Snickers bar is generally between 9 and 12 months, assuming proper storage. Mars maintains rigorous quality control protocols, including sampling every batch for flavor consistency, structural integrity, and microbiological safety. Automated inspection systems use vision technology to detect misaligned bars, incomplete coatings, or wrapper defects, automatically removing flawed units from the line. Throughout the plant, hygiene is paramount, with clean-in-place systems for all equipment and strict allergen controls to ensure product safety. What makes Snickers particularly remarkable is how such a complex, multi-layered treat can be produced with such uniformity at an industrial scale. From raw peanuts and liquid caramel to perfectly wrapped bars stacked on pallets, every aspect of production is optimized for speed, precision, and global distribution. Millions of Snickers bars roll off the line each day, each one representing a perfected system of mass food manufacturing. It all begins with cocoa beans for Hershey's chocolate, which are the fundamental raw ingredient in all chocolate. Hershey sources its cocoa beans primarily from West Africa, countries like Côte d'Ivoire and Ghana, where the climate, soil, and traditional farming practices produce high-yield crops with desirable flavor characteristics. Once harvested, the cocoa beans are fermented in banana leaf-lined piles and dried under the sun before being packed in jute bags and shipped across the ocean to Hershey's production facilities in the United States. Upon arrival, the beans are subject to rigorous testing. Random samples from each shipment are roasted and analyzed for aroma, acidity, moisture content, and potential contaminants. Approved beans are stored in large silos, sorted by origin and quality grade. From here, the first major step in the chocolate making process begins roasting. Roasting is not just about cooking the beans, it's a chemical transformation that unlocks the complex flavors hidden within the cocoa nibs. The beans are fed into large, rotating drum roasters or continuous belt roasters and exposed to carefully controlled dry heat at temperatures between 250 degrees and 300 degrees for 20 to 30 minutes. This Maillard reaction develops the chocolate flavor while drying the beans further and loosening the outer shells. The duration and temperature of the roast are adjusted depending on the origin and size of the beans, with constant airflow and humidity control. After roasting, the beans are cooled and sent through cracking machines that break them open, separating the brittle outer shells from the inner nibs. The broken shell pieces are removed through winnowing, a process that uses airflow to lift away the lighter shells, leaving behind clean cocoa nibs. These nibs are the essence of chocolate, rich in cocoa solids and cocoa butter. The nibs are then ground into a thick, gritty paste called chocolate liquor, not to be confused with alcohol. This step is performed in heavy-duty grinding mills, such as stone refiners or steel disc mills, which apply intense pressure and friction. As the nibs break down, their fat melts, turning the mass into a thick, flowing fluid. At this point, the chocolate liquor is still unrefined, with a coarse texture and bitter flavor. For milk chocolate, Hershey adds a blend of sugar, milk ingredients, and sometimes vanilla and lecithin to the chocolate liquor. One of the defining features of Hershey's milk chocolate is its use of fresh fluid milk that is processed in-house. Unlike European chocolates that often use powdered or condensed milk, Hershey pioneered a method of processing fresh milk into milk crumb, a dehydrated mixture of milk solids and sugar, using vacuum cooking and drum drying techniques. This milk crumb, with its slightly tangy cooked flavor, contributes to the uniquely Hershey taste. The chocolate liquor, milk crumb, and sugar are blended in large stainless steel mixing tanks, forming a uniform paste. At this stage, the mixture is still coarse and gritty, unsuitable for final chocolate texture. It must be refined. The refining process involves passing the chocolate mass through a series of roller mills, typically 5-roll refiners that reduce the particle size of the solids to less than 30 microns. The goal is to achieve a silky smooth mouthfeel without any noticeable graininess. Once refined, the chocolate enters the conching phase, one of the most critical steps in flavor development. Conching is a process of continuous mixing, aerating, and heating the chocolate over many hours to improve its taste and texture. Hershey's uses a combination of traditional longitudinal conches and modern rotary conches that knead the chocolate at controlled temperatures, typically between 120 degF and 180 degF. This process helps evaporate undesirable volatile acids, mellow bitter notes, and fully integrate the milk and cocoa flavors. The viscosity and aroma are fine-tuned during this stage through mechanical shearing and time adjustments. Following conching, the chocolate undergoes tempering, a heat treatment process that ensures the final product has a smooth, glossy finish and a crisp snap when broken. Cocoa butter can crystallize in several forms, but only one, known as Form 5, gives chocolate its ideal physical properties. Tempering involves heating the chocolate to about 115 degrees, then cooling it down to around 80 degrees, and finally reheating it slightly to about 88 degrees to promote the formation of stable crystals. This carefully controlled cycle is performed in continuous tempering machines, which maintain consistent temperatures and flow rates. Tempered chocolate is now ready for molding. Hershey's uses high-speed molding lines where liquid chocolate is deposited into polycarbonate molds in precise weights. The molds are vibrated to remove air bubbles and ensure even distribution. For classic bars like the Hershey's Milk Chocolate Bar, the molds are designed with the familiar rectangular break-apart sections embossed with the Hershey name. Once filled, the molds travel through long refrigerated cooling tunnels where the chocolate solidifies into its final form. As the bars cool, they are monitored by temperature sensors and mechanical feelers to ensure proper release. When fully set, the bars are automatically ejected from the molds and conveyed to the wrapping station. Modern wrapping equipment is synchronized with bar output and uses roll-fed film that is printed with the Hershey's branding, ingredients, and expiration codes. Wrappers are folded and sealed using rotary crimpers, and a barcode is applied for tracking. Wrapped bars are then grouped into cartons or display trays using robotic pick-and-place systems and conveyed to the end-of-line packaging area. Here, cases are formed, filled, and sealed before being palletized by automated arms. Each pallet is shrink-wrapped and scanned into inventory, ready for transport to distribution centers across the country and around the world. Throughout the entire process, quality control is a constant presence. Samples are pulled from every batch for testing. Sensory panels evaluate flavor and aroma, while lab technicians measure moisture content, fat percentage, and microbial levels. Machine vision systems inspect each bar for dimensional accuracy and surface defects. Metal detectors and X-ray machines scan for foreign objects, while thermal imaging cameras check for temperature compliance at various stages. Behind the scenes, Hershey's factories are tightly integrated with computerized control systems that track every ingredient, process parameter, and output metric in real time. From ingredient blending to chocolate tempering and bar wrapping, programmable logic controllers and supervisory control and data acquisition systems coordinate the hundreds of motors, valves, conveyors, and sensors that make up the line. These systems not only maximize efficiency and reduce downtime, but also ensure that each bar tastes the same as the one before it. Once packaged and palletized, Hershey's bars enter the post-production logistics chain. Distribution centers maintain climate-controlled storage to preserve chocolate integrity. Trucks are loaded according to first-in, first-out scheduling, and GPS tracking systems ensure timely delivery to retailers, vending machine operators, and wholesalers. Chocolate bars are especially sensitive to heat and humidity, so strict environmental controls are observed throughout transportation and warehousing to prevent melting or bloom. Interestingly, the Hershey flavor that many Americans recognize and even associate with nostalgia is not accidental. It's the result of deliberate formulation choices, particularly in how milk is treated during production. Some analysts believe the signature, slightly sour or tangy flavor found in Hershey's milk chocolate comes from the breakdown of milk fats into butyric acid during controlled lipolysis, an effect that differentiates Hershey's from creamier European chocolates. This flavor profile has become a cultural benchmark in the United States, deeply woven into American food identity. Despite decades of innovation and scaling up, the heart of Hershey's chocolate production still echoes the vision of its founder: to make high-quality milk chocolate affordable and accessible to everyone. With more than a century of history and tens of millions of bars produced annually, Hershey's remains a pioneer in automated food manufacturing, exemplifying the blend of tradition, precision engineering, and industrial food science. From bean to bar, the production of Hershey's chocolate is a story of transformation, driven by technology, but grounded in flavor. Toblerone chocolate production begins with the sourcing and intake of its core raw materials: cocoa mass, cocoa butter, sugar, milk powder, honey, almonds, and soy lecithin as an emulsifier. The distinct taste of Toblerone, known for its smooth Swiss milk chocolate interspersed with chewy nougat and honey almond notes, relies on both the precision of ingredient handling and the consistency of every preparation stage. The factory intake process starts with the arrival of these ingredients at the manufacturing plant's loading bay. Each ingredient is stored and transported under specific conditions tailored to its nature. For example, cocoa mass and cocoa butter, which are highly sensitive to temperature and oxidation, are delivered in thermally stabilized containers that keep them in a semi-solid state. Upon arrival, these containers are immediately transferred into insulated storage tanks inside the facility to prevent exposure to ambient air and humidity. These tanks are purged with inert nitrogen gas to minimize oxidation and preserve flavor integrity. Milk powder, sugar, and lecithin arrive in sealed food-grade sacks or large bulk bins and are lifted by pneumatic suction systems into silo units for temporary storage. Before anything enters the production stream, comprehensive quality assurance testing is conducted. Samples from each delivery are checked for microbiological safety, color, flavor, moisture content, and texture. Specialized equipment such as near-infrared spectrometers and rotary viscometers are used to assess these parameters in real time. Once verified, the production of the chocolate base begins. This base, which will serve as the core medium for all Toblerone bars, is created by combining cocoa mass, cocoa butter, sugar, and milk powder. Each of these components is dispensed into high-capacity stainless steel mixers in precise ratios dictated by the Toblerone formulation. These mixers are automated and fitted with load cells to ensure that each ingredient is weighed to the gram before being introduced to the blend. The contents are mixed at low speed to ensure a homogeneous distribution of particles without excessive aeration. This preliminary mixture, however, is far from the final silky chocolate. At this stage, the texture is coarse and grainy. To refine it, the mix is fed into a 5-roll refiner. The 5-roll refiner is a massive piece of machinery consisting of 5 horizontally aligned steel rollers that compress and shear the chocolate particles down to a size between 18 and 25 microns. This reduction in particle size is critical for mouthfeel. If particles remain larger than 30 microns, the human tongue perceives a gritty texture. Below 20 microns, the chocolate begins to melt smoothly and luxuriously in the mouth. During refining, sensors continuously monitor the gap between rollers and particle fineness using real-time laser diffraction analysis. Excessive refining can result in overheating or fat separation, so the temperature of each roller is actively cooled and monitored to maintain uniform conditions. The refined paste exits the refiner as a silky, thick, and slightly warm material, ready for the next stage, conching. Conching is the step where Toblerone's flavor is truly developed and its texture perfected. The conche machine is a large enclosed vessel that contains mechanical arms or rotors that knead the chocolate mass for several hours. This process serves multiple purposes. First, it evaporates unwanted volatile compounds, such as acetic acid or aldehydes, that may have formed during roasting or refining. Second, it distributes the cocoa butter evenly around each solid particle, coating them thoroughly and improving the overall flow behavior of the chocolate. The conching process typically lasts between 6 and 12 hours, depending on the batch size and the desired profile of the chocolate. During this time, emulsifiers such as soy lecithin are added to reduce the chocolate's viscosity without increasing the fat content. This makes the chocolate easier to mold and coat, while also enhancing its melt-in-the-mouth properties. It is also during conching that the iconic honey and nougat flavor notes of Toblerone begin to be layered in. Honey is added in measured amounts, not just for sweetness, but also to contribute to the product's distinct aroma and chewiness once combined with nougat. The factory conching process uses controlled heat, usually between 45 degrees Celsius and 80 degrees Celsius, to keep the cocoa butter in a liquid state. Temperature control is crucial. Too hot, and the chocolate risks burning or developing off flavors. Too cold, and the process slows, failing to drive off sufficient moisture. Modern conches are equipped with real-time pH, moisture, and volatile compound sensors that feed back into the control system, allowing operators to adjust mixing speed, arm pressure, or temperature on the fly. Once the conching is complete, the resulting chocolate is an ultra-smooth, shiny, and aromatic mixture. It is pumped into jacketed holding tanks that keep it at a stable temperature of around 30 to 32 degrees Celsius, ideal for downstream processes such as tempering and molding. These tanks are constantly agitated to prevent fat separation and crystallization. The next stage, tempering, is a pivotal process that controls the crystal structure of cocoa butter in the chocolate. Cocoa butter can crystallize in several different forms, but only one form, Form V, produces chocolate that is glossy, firm, and resistant to melting at room temperature. Achieving this form requires carefully heating and cooling the chocolate through a specific temperature curve. Tempering is done in continuous tempering machines where chocolate is first heated to around 45 degrees Celsius to eliminate all previous crystal formations, then cooled down to approximately 27 degrees Celsius to initiate the formation of stable seed crystals. The chocolate is then gently reheated to around 31 to 32 degrees Celsius to eliminate any unstable forms and maintain only the desired crystalline structure. These temperature transitions are tightly controlled by heat exchangers and thermal sensors, which ensure that the flow and crystallization kinetics of the chocolate are kept within narrow limits. With the tempered chocolate now perfectly conditioned and held at its ideal working temperature, it's time to move into one of the most distinctive and meticulously engineered steps of the entire Toblerone production process: molding the chocolate into its iconic triangular bar shape. This is not simply about pouring chocolate into a unique mold. It involves a detailed and highly synchronized series of movements designed to maintain structural integrity, precision alignment, and uniformity across millions of units. The Toblerone mold consists of a series of equidistant triangular cavities arranged in a straight line. Each mold cavity is designed to hold a single triangle of the bar, with narrow necks between them that allow for precise chocolate flow while ensuring each triangle remains individually defined yet conjoined. These molds are made of food-safe, high-strength polycarbonate and are preheated to prevent premature cooling when the liquid chocolate is deposited. Preheating ensures the chocolate flows evenly into every corner of the mold without setting too quickly, which could cause defects like air bubbles or incomplete shapes. Before chocolate enters the mold, the entire cavity array is vibrated at a high frequency using a precision-controlled shaker system. This vibration helps eliminate trapped air, allowing the chocolate to settle smoothly and evenly. The vibrating stage is calibrated to match the viscosity of the chocolate in real time, using inline sensors that monitor the chocolate's flow behavior. Any slight deviation in viscosity can affect how well the chocolate fills the narrow base points of the triangular molds, so the system adjusts shaker speed accordingly. Once the molds are filled, they pass under a leveling scraper to ensure the chocolate surface is perfectly flat along the bottom of the bar, which will ultimately become the base. A second, shorter vibration cycle occurs after this to further consolidate the chocolate and ensure all suspended particles, especially small bits of nougat or almonds, are evenly dispersed within each triangle. If the nougat or honey pieces were to settle unevenly during this stage, it would create inconsistent textures and affect quality. At this point, the filled molds are slowly moved into a multi-zone cooling tunnel. The tunnel is designed to gradually reduce the temperature of the chocolate from around 32 degrees Celsius to below 10 degrees Celsius over the course of several minutes. The zones begin with gentle ambient cooling, progressing through stages of increasingly chilled air, circulated by high-efficiency fans. The slow drop in temperature is crucial. If chocolate is cooled too rapidly, it can develop stress fractures, surface bloom, or uneven crystallization. The cooling system is monitored constantly using digital thermometers, hygrometers, and flow sensors to guarantee uniform airflow and humidity across every inch of the tunnel. As the molded bars pass through each zone, the cocoa butter crystallizes uniformly into the stable Form V lattice structure, locking in glossiness and snap. This stage also causes the chocolate to shrink slightly away from the walls of the mold, which facilitates easy demolding later. Once the bars exit the cooling tunnel, they are still within the molds, but now fully solidified and dimensionally stable. Next, the demolding process begins. The molds are inverted onto conveyor belts equipped with soft silicone pads that cushion the fall of each bar as it's ejected. Demolding can be done either pneumatically, where jets of compressed air push the back of the mold to dislodge the bar, or mechanically, using plungers that gently press the chocolate out. In either case, sensors monitor the success rate of ejection, and any mold that fails to release the bar is automatically sent to a rework line. Once the Toblerone bars are released from the molds, they are briefly passed through an inspection station where machine vision systems check for mold, fill consistency, breakage, surface defects, and geometric conformity. High-resolution cameras and laser profiling tools compare each bar against stored 3D models. Bars that fall outside tolerance thresholds are marked for reprocessing, where they will be remelted and reintegrated into the production line. The successfully molded and cooled bars now enter the next phase, packaging. Before wrapping, each bar passes through a controlled dehumidification tunnel. This step is critical for preventing condensation during packaging, which could lead to microbial growth, sugar bloom, or spoilage. The dehumidifier maintains an environment below 30% relative humidity and gently warms the air around the chocolate to just above ambient temperature, allowing any moisture on the surface to evaporate without melting the chocolate. Once surface conditions are stabilized, the Toblerone bars move to the wrapping station. Here, the bars are individually picked and aligned onto a high-speed belt, where the characteristic triangular cardboard sleeve is automatically wrapped around each one. The sleeves are die-cut from pre-printed cardboard stock, folded precisely, and glued using food-safe adhesive. Each wrap is barcoded and batch-coded in real time, using inkjet printers synchronized with the production software. After the sleeve is applied, some product variations receive a foil wrapping beneath the cardboard. The foil is cut from gold-colored rolls and folded tightly around the chocolate by robotic arms using pre-programmed pressure patterns that ensure coverage without crushing the delicate points of the triangles. The foil serves as an oxygen and light barrier to prolong shelf life, especially for Toblerone products destined for warmer climates or long export journeys. Every wrapped bar is now scanned and weighed by automated inspection stations. Any unit that falls below or exceeds target weight, accounting for chocolate and packaging, is removed from the line for manual inspection. Those that pass all checks are sorted into bundles depending on product format: single bars, multi-packs, or gift sets. The bars are grouped into cartons by pick-and-place robots. These robots use suction cups and soft grippers to avoid damaging the points of the chocolate triangles. The cartons are then sealed, labeled with lot and traceability data, and stacked into master cases. Each master case is assigned a tracking code and loaded onto pallets using robotic palletizers programmed for maximum cube efficiency and stability. These pallets are then wrapped with stretch film and stored in temperature-controlled warehouses. Warehouse conditions are kept between 16 degrees Celsius and 18 degrees Celsius, with less than 50% humidity to prevent bloom and preserve texture. Pallets are logged into a central warehouse management system that coordinates batch rotation using FIFO principles, ensuring freshness upon delivery. Now that the Toblerone bars have been successfully molded, inspected, and packaged into their iconic triangular sleeves, the next stages of the factory operation transition from chocolate engineering into full-scale logistics, global adaptation, and product diversification, all of which require just as much planning, precision, and technical orchestration as the earlier phases of the chocolate creation itself. The journey from packaged bar to store shelf begins in the factory's outbound logistics area, where every finished pallet is scanned into the warehouse management system. The system integrates with enterprise resource planning software to track inventory levels, prioritize shipping based on destination climate, customs requirements, and expiration dates, and coordinate loading dock activity to maximize efficiency and avoid bottlenecks. At this point, temperature control becomes a dominant concern. Because chocolate is sensitive to thermal shock and prolonged exposure to high humidity or temperatures, all shipments are required to pass through insulated loading bays equipped with temperature buffering systems. These systems maintain consistent conditions even as trucks are loaded, preventing any temporary environmental spikes that might affect product integrity. For shipments destined for nearby distribution centers within a 200-kilometer radius, standard refrigerated trucks are used. These trucks are pre-cooled to the exact storage requirements, typically 16 to 18 degrees Celsius, and each one is fitted with temperature loggers and GPS tracking units that upload data to the central logistics server in real time. Any deviation in internal truck temperature during transit is flagged automatically, prompting quality control checks upon arrival. For export shipments, particularly to regions like Southeast Asia, Africa, or South America, Toblerone products are loaded into refrigerated shipping containers with independent power units, ensuring continuous cold chain conditions during ocean transport that may span up to 3 weeks. Each pallet is labeled with multiple identifiers, including product code, lot number, production time, line number, and temperature certification. These labels are printed using thermal transfer printers that embed RFID chips or scannable QR codes to allow full traceability. This level of detail is critical not only for internal logistics and recall management, but also to meet the regulatory requirements of import authorities in different countries. For instance, Gulf countries may require halal certification to be attached to the consignment, while Japan may demand documentation showing compliance with their unique food additive regulations. Toblerone's global logistics strategy is thus heavily embedded in regulatory compliance, with dedicated teams managing certification, customs documentation, and export logistics. Back within the facility, the production line doesn't operate in isolation. It's part of a broader, synchronized network of production scheduling. Toblerone is not produced as a single SKU, but in a wide variety of formats, each requiring slightly different processing configurations. These include the classic 100-gram bar, 50-gram snack bar, 360-gram gifting box, tiny 12.5-gram miniature pyramids, and specialty editions like white chocolate or dark chocolate variations. Each variation has a specific recipe profile, mold configuration, cooling requirement, and packaging format. Switching between variants requires a carefully managed process known as a changeover. A changeover begins with a complete emptying of all hoppers, pipelines, and depositors currently filled with one chocolate variant. The equipment is flushed using tempered cocoa butter or neutral chocolate mass to clear residual flavors and prevent cross-contamination. Then, the line undergoes a clean-in-place cycle involving detergent wash, water rinse, and final steam sanitization. Sensors measure residual proteins and fats in rinse water to confirm cleanliness. Only after quality control confirms a clean system does the new variant's ingredients enter the production stream. Changeovers also affect the molding system. For example, miniature Toblerone shapes are molded using smaller polycarbonate trays that are swapped in with robotic carriage systems. These molds pass through the same preheating, filling, vibration, and cooling steps as their larger counterparts, but on accelerated cycles due to their reduced volume and mass. The packaging system, too, must adapt. Larger bars require stronger folding cartons with inner trays, while minis are often flow-wrapped and placed into pouches or mixed assortment boxes. To handle this, the line includes modular packaging equipment that can be reprogrammed within minutes using preset SKU profiles. Operators scan a barcode for the new SKU, and all conveyor speeds, arm timing, and print data update automatically. A parallel stream of work takes place in Toblerone's research and development lab, often co-located with the factory or within the company's broader innovation campus. Here, food technologists and process engineers develop new flavor profiles, test alternative sweeteners, and design special edition runs tailored to holidays, partnerships, or regional taste preferences. For example, a limited edition bar infused with salted caramel may require different sugar crystallization controls, or a Ramadan edition might include date extract and modified packaging with Arabic text. Pilot-scale batches are created on miniaturized versions of the factory equipment, allowing experimentation without interrupting commercial-scale output. Every new recipe that graduates from R&D to factory production goes through a phase called scale-up validation. During this stage, the formulation is first made on a semi-commercial line capable of producing thousands of units per hour, and multiple parameters are tested: ingredient behavior under continuous agitation, flow characteristics during tempering, molding fidelity in standard production molds, and thermal stability during cooling. If the results meet the product development benchmarks, full-scale production is approved. Another important dimension of Toblerone's operation is environmental stewardship and factory sustainability. In recent years, the facility has upgraded many of its core systems to reduce carbon footprint, minimize waste, and improve energy efficiency. The chocolate tempering machines now utilize closed-loop thermal exchange systems that recycle cooling energy from one process to another. The air handling systems in the cooling tunnels and clean rooms have been upgraded to variable speed drives and high-efficiency particulate air filtration, significantly cutting energy usage while maintaining product safety. In terms of ingredient sustainability, Toblerone's cocoa is sourced under certified ethical sourcing programs, which ensure that the farms supplying cocoa beans are paid fairly, do not use child labor, and implement agroforestry practices that support biodiversity. These cocoa beans are processed into cocoa mass and cocoa butter by contract processors who follow Toblerone's strict quality and sustainability protocols, including traceability from farm to factory. The almonds and honey, too, are held to exacting standards. Almonds are supplied by certified orchards in California or the Mediterranean, sorted for size and oil content. Honey is sourced with attention to floral origin, ensuring a consistent flavor batch after batch. In-house testing includes pollen analysis, sugar spectrum fingerprinting, and moisture checks. This commitment to sourcing excellence reinforces the brand's identity as a premium Swiss chocolate. Finally, consumer safety and food compliance are at the core of every step of the Toblerone factory. All areas of the facility are subject to strict zoning protocols, separating raw ingredient handling from finished product areas to prevent contamination. Staff undergo regular hygiene training, wear full protective clothing, and enter through sanitation airlocks that include hand washing, boot scrubbing, and compressed air garment cleaning. Equipment is built to hygienic design standards, with no exposed threads, crevices, or moisture traps. Quality assurance checkpoints occur at dozens of locations throughout the line. Metal detectors are installed post-packaging to catch any foreign material. Check weighers ensure that each unit falls within exact mass tolerances. Barcode scanners verify packaging accuracy. And final batch records are signed off by a trained quality technician before any shipment is released. Even the slightest anomaly, an over-tempered batch, a slightly tilted mold, a misaligned wrapper, is caught, logged, and addressed through a root cause analysis process. Every detail matters because Toblerone is not simply a chocolate bar. It's a global symbol of quality, tradition, and precision engineering. What looks like a single, satisfying triangle is actually the result of hundreds of synchronized decisions, operations, and technologies that function in harmony to deliver an unchanging standard of excellence. With the full-scale production, molding, packaging, and international logistics already finely tuned, the final stages of Toblerone's manufacturing process revolve around final distribution, continuous improvement protocols, consumer-facing customization, and digital integration that modernizes how quality and efficiency are sustained across an ever-growing global demand. Once pallets of finished, labeled, and verified Toblerone products are ready for shipment, they enter the outbound logistics management system, where real-time data on shipping routes, order queues, and warehouse availability determine where each batch goes next. The system doesn't just track inventory, it optimizes routes based on transportation cost, shelf life preservation, retail replenishment cycles, and sales forecasts provided by global distribution partners. Whether a shipment is bound for a Swiss airport duty-free zone, a North American grocery chain, or an e-commerce fulfillment center, its path is selected based on minimizing transit time and maintaining perfect storage conditions. Each truck or container that leaves the factory is accompanied by digital and printed documentation that includes compliance declarations, temperature logs, ingredient traceability records, and destination-specific export certificates. These are often required at borders for customs clearance, particularly in markets with strict regulations around food labeling, allergens, or religious dietary requirements like halal or kosher certifications. The factory's compliance team works in sync with shipping personnel, constantly updating their records as international regulations evolve. Inside the production facility itself, continuous improvement is embedded at every level. Daily performance metrics are posted on digital displays throughout the production floor, tracking everything from machine uptime and output per hour to defect rates, waste percentages, and energy usage. Operators have access to touch panel controls that allow them to report faults or initiate adjustments on the fly. When an anomaly is detected, it's logged in a root cause tracking system that prompts follow-up from engineering or quality assurance teams. This immediate feedback loop is designed to prevent small issues from becoming systemic problems. Preventive maintenance also plays a major role in sustaining Toblerone's high production standards. Every piece of equipment in the line, from chocolate mixers to automated packers, is tagged with a maintenance schedule integrated into the plant's CMMS. Operators are prompted automatically when a belt needs replacement, a blade needs sharpening, or a motor requires lubrication. By minimizing unplanned downtime, the factory ensures consistency in output and avoids any deviation from scheduled production volumes. Consumer customization is another frontier in Toblerone's manufacturing strategy. For promotional seasons, corporate gifting campaigns, or regional celebrations, Toblerone offers limited edition bars with printed names, holiday messages, or even national flag motifs. Reese's Peanut Butter Cups begin with the bulk delivery of raw peanuts to the factory's intake silos, where they are gravity-fed into the initial sorting system. These peanuts are inspected mechanically, using a combination of vibrating sieves and optical sorters to remove any debris, underdeveloped kernels, or foreign materials. Once sorted, the peanuts move via enclosed conveyors to massive gas-fired rotary roasters. These roasters tumble the peanuts at temperatures ranging from 160 to 180 degrees Celsius for up to 30 minutes, depending on the batch specifications. Uniform roasting is critical, as it directly impacts the flavor profile of the peanut butter core. Immediately after roasting, the peanuts are dropped into rapid cooling bins to halt the cooking process. Once cooled, they're transported to a dry de-skinning machine, where rubber-lined rollers strip the outer skins, which are then removed via airflow separators. The cleaned roasted peanuts are directed into hoppers that feed them into industrial grinders. The first stage produces a coarse paste, while the second stage refines this paste into a smooth, semi-solid mass with just enough texture to give Reese's its signature, slightly grainy peanut butter. At this stage, the peanut paste is blended with dextrose, salt, and a small quantity of vegetable oil stabilizers in jacketed mixing tanks. These tanks are equipped with high-torque agitators that ensure uniform mixing and prevent separation. The peanut butter is then pumped into storage tanks held at a steady 40 degrees Celsius to maintain pourability, with recirculation loops preventing oil separation. While the peanut butter is being prepared, the chocolate coating is simultaneously processed in a different section of the plant. Solid chocolate blocks arrive in insulated pallets and are broken down into manageable chunks by automated crushers. These chunks are melted in conical tempering kettles, where the chocolate is cycled through precise temperature phases. Heating to 45 degrees Celsius to dissolve fat crystals, cooling to 27 degrees Celsius to encourage type 5 crystal formation, and then reheating slightly to 30 to 31 degrees Celsius to prepare for molding. This tempered chocolate is fed through stainless steel piping with heated jackets into the deposition zone. The chocolate is deposited into paper-lined plastic molds using servo-controlled nozzles. The molds are pre-fitted with pleated paper cups, automatically dispensed and placed by robotic arms. The bottom layer of chocolate is dispensed in a circular motion to form a consistent base. The molds are gently vibrated on a plate to spread the chocolate evenly and eliminate air bubbles. Once the bottom shell is semi-set, the peanut butter is deposited in the center using another set of volumetric piston fillers. Each dollop is carefully controlled to ensure it stays centered and does not bleed into the side walls, which would prevent the top chocolate layer from sealing properly. The peanut butter is slightly cooler than the chocolate to preserve its form as it's deposited. The top chocolate layer is applied almost immediately after the peanut butter centers are deposited. Another set of nozzles applies tempered chocolate to fully enrobe the filling, again followed by brief vibration to ensure complete coverage and smooth surface finish. This layered structure of chocolate, peanut butter, and chocolate is the signature of every Reese's cup, and the volumes are calibrated down to the milliliter. Next, the filled molds enter a tiered cooling tunnel. This tunnel is divided into climate zones, with each zone dropping in temperature by small increments, from 20 degrees Celsius down to around 8 degrees Celsius, over the course of 15 to 18 minutes. This gradual cooling prevents thermal shock, which could cause cracking or separation between the chocolate and filling. Each zone is equipped with air circulation fans, refrigeration coils, and humidity control systems to ensure perfect crystallization of the chocolate. After the cooling process is complete, the now fully formed Reese's cups are ejected from their molds using a pneumatic plunger system that pushes from beneath the mold cavities. The cups remain in their paper liners and are transferred to conveyance lanes for wrapping. At this point, the cups are still exposed and vulnerable to environmental conditions, so the transfer occurs within a controlled, filtered air enclosure to prevent contamination. The wrapping process uses horizontal flow wrappers. Each Reese's cup is aligned via guide rails and funneled into individual wrapping lanes. Printed foil is unwound from rolls and cut to size by rotary knives. The cup is pushed onto the foil by a mechanical arm, and the foil is folded and sealed around the candy using heat-sealing jaws that close in fractions of a second. The wrapped cups are then printed with batch codes and expiration dates using inkjet or thermal printers. For king-size or multi-cup packages, the single wrapped cups are automatically grouped and loaded into larger overwrap film using a secondary wrapping machine. These packages are then loaded into display cartons by robotic pick-and-place arms that orient each unit for retail presentation. These cartons are glued or tab sealed, then labeled with product identifiers, shipping information, and QR codes for traceability. Before packaging is finalized, random samples are pulled from each production batch and sent to quality assurance labs. Here, technicians weigh each cup, examine chocolate gloss and thickness under calibrated lighting, and use penetrometers to test the firmness of the peanut butter. They also cut cross-sections of the cups to visually inspect layering uniformity and check for air gaps or structural flaws. Once cleared, finished cartons are palletized using robotic stacking systems that build stable load units based on truck optimization software. Each pallet is stretch wrapped and labeled with RFID tags that track its origin, contents, and destination. These pallets are loaded onto climate-controlled trucks that maintain the cargo area between 10 degrees Celsius and 22 degrees Celsius, preventing chocolate bloom or melting during transport. Even after the cups leave the factory, Hershey maintains control over their handling through advanced logistics software. This platform integrates sales forecasts, retailer data, and shipping conditions to prioritize inventory rotation and ensure that product closest to expiration is delivered first. Warehouses use automated pick systems and real-time barcode scanning to manage stock. In addition to the standard production line, seasonal Reese's cups, like pumpkin or heart shapes, are produced using interchangeable mold plates. These specialty shapes require adjustments in chocolate and filling deposition to accommodate varied volume and geometry. The same precision is applied to these runs, though the visual inspection is even more rigorous due to complex shapes. Flavor innovation is handled through a separate R&D pipeline. Variants like white chocolate or dark chocolate cups require their own tempering parameters and material handling systems to prevent cross-contamination. These are produced in small trial batches on modular production lines until formulations are approved for full-scale production. From a sustainability perspective, Hershey continuously works to reduce energy and material waste. Chocolate tempering kettles use thermal recirculation systems to recover heat energy, while the roasting exhaust is captured and scrubbed for reuse in preheating systems. All peanut skins, chocolate trimmings, and off-spec cups are collected and either reprocessed or converted into animal feed and energy through biodigesters. This entire system, roasting, grinding, tempering, depositing, cooling, wrapping, inspecting and shipping, operates in a tightly synchronized loop, monitored by real-time factory control software. Supervisors can access dashboards showing throughput, downtime, temperature profiles, and ingredient usage. Alerts notify operators of any deviations from specification, and corrective actions are logged for traceability. Every Reese's cup, whether it's a classic 2-pack or a seasonal novelty, is the result of layered processes fine-tuned to deliver the exact same flavor and texture every time. From the precise ratio of peanut to salt, to the sheen on the chocolate, to the shape of the paper liner, all of it is the product of exacting industrial craftsmanship. Mars chocolate bar production starts with the arrival of key ingredients at the facility: raw cocoa mass, cocoa butter, sugar, skimmed milk powder, lactose, glucose syrup, and proteins used in the nougat layer. All ingredients are subject to strict quality control before entering the production line. Cocoa mass and butter are delivered in solid block form, stored in climate-controlled zones, and tested for fat content, aroma, and particle size. Sugar arrives in bulk and is transferred pneumatically into silos. Milk powders are delivered in sealed containers, sampled for moisture and purity, then funneled to automated dosing stations. The chocolate phase begins with tempering and mixing. Cocoa mass and cocoa butter are first melted in stainless steel, jacketed tanks at precise temperature ranges, typically between 45 degrees Celsius to 50 degrees Celsius. This molten chocolate mixture is sent into high-capacity blenders, where sugar, milk powders, and lactose are added. The mixing process creates a coarse paste which then undergoes refining. Refining is done using 5-roll refiners, massive machines where the chocolate paste passes through a series of increasingly narrow steel rollers. These rollers compress the paste down to a fine particle size between 20 to 30 microns. This size range ensures that the final chocolate feels silky and not gritty. Sensors monitor the output continuously for particle size and adjust roller pressure accordingly. The refined paste is moved into conching machines, where it's heated and agitated for several hours. Conching removes volatile acids and moisture while developing flavor and viscosity. Emulsifiers like soy lecithin are added during this phase to control flow behavior. The conched chocolate is then pumped into holding tanks kept at 30 to 32 degrees Celsius, ready for use in barcoding and mold filling. In parallel, the nougat layer is being produced in a different section of the factory. Mars's nougat starts by mixing sugar, glucose syrup, and water in large cookers. This mixture is heated to form a syrup, which is transferred to industrial aerators. Here, whipped protein, often derived from egg whites or hydrolyzed soy protein, is added. The high-speed aerators incorporate air into the mix, giving nougat its light, chewy texture. Once whipped, the nougat is enriched with milk powder, fats, and flavoring components to build creaminess and mouthfeel. The warm, aerated nougat is extruded onto a continuously moving conveyor belt as a wide, flat slab. As it travels down the line, it is cooled by overhead airflow units to partially set its structure. Once firm enough, the nougat sheet is trimmed to a uniform width using high-speed rotary blades and moves to the caramel deposition stage. Mars caramel is produced using continuous vacuum cookers. Sugar, glucose syrup, and milk ingredients are heated under vacuum to lower the boiling point, preserving soft texture and rich dairy flavor. Once the caramel reaches the desired consistency, it is deposited as a thin, even layer over the traveling nougat base. This layered slab now resembles the cross-section of a Mars bar before chocolate coating. Cooling tunnels set the caramel onto the nougat layer using a staged drop in temperature from ambient to around 10 to 12 degrees Celsius. Once the slab is fully set, it moves to ultrasonic cutters. These high-frequency blades cut the slab into bar-length segments with minimal compression, maintaining clean edges and uniform size. Each bar now contains a core of structured nougat and a top layer of soft caramel, and is ready for chocolate coating. The next stop is the enrobing line. Each bar is placed onto a perforated conveyor belt and passes through a chocolate curtain, molten tempered chocolate falling in a continuous sheet. A bottoming roller ensures the underside is coated first. Air knives blow off excess chocolate and shape the final bar profile. Edge trimming guides ensure the sides are evenly coated without pooling. The entire chocolate coating process is conducted at controlled temperatures, usually around 30 degrees Celsius, to maintain chocolate viscosity and gloss. Once coated, the bars enter a long, refrigerated cooling tunnel. This tunnel gradually lowers the temperature over multiple zones, ensuring that the chocolate sets smoothly without cracks or bloom. Cooling takes roughly 12 to 15 minutes. Humidity is strictly controlled throughout to prevent condensation on the bars. Upon exiting the cooling tunnel, the bars are transferred to the wrapping station. Each bar is aligned into feeding lanes and enters a horizontal flow wrapper. Printed packaging film is unwound and formed around each bar. The wrapper is sealed using heat and pressure at the ends and along the back. Prior to sealing, the package interior may be flushed with nitrogen gas to remove oxygen and extend shelf life. Barcodes, batch codes, and expiry dates are printed in real time using high-speed inkjet printers. Cameras verify print legibility and seal integrity, and any faulty packages are ejected from the line. Accepted bars are automatically grouped into cartons, 12, 24, or 36 count configurations, depending on destination and retail requirements. Cartons are sealed with glue or interlocking flaps and labeled with destination codes. Palletizing robots stack cartons onto wooden or plastic pallets using algorithms that maximize load stability and cube efficiency. Once stacked, the pallets are stretch wrapped with plastic film and labeled with RFID tags containing tracking and batch data. These pallets are transported via forklifts or automated guided vehicles to temperature-controlled storage areas. Inventory management systems track product age and availability in real time. Orders are picked and dispatched using a just-in-time system integrated with retailer demand signals and distribution schedules. In addition to core Mars bars, the same line can be configured to produce variations such as fun size, twin pack, or regional editions. Changeovers involve switching cutting equipment, recalibrating depositor heads, and swapping packaging materials. This flexibility allows Mars to meet seasonal demand spikes or promotional formats without building entirely new production lines. Throughout the process, dozens of sensors, cameras, and feedback systems maintain quality. Chocolate viscosity is tracked with inline viscometers. Weight checks are performed on each bar using precision scales, and metal detectors ensure product safety. Quality control technicians also pull random samples hourly to inspect cross-sections, flavor, and mouthfeel. Sensory testing panels taste test bars daily to ensure consistency. Waste is minimized through rework systems. Off-spec nougat and caramel are reprocessed when possible, and chocolate trimmings are collected and remelted for future batches. Scraps unsuitable for reuse are converted to animal feed or processed through waste-to-energy systems. Sustainability initiatives have also taken hold. Mars uses responsibly sourced cocoa certified by third-party organizations and invests in water reduction systems and energy recovery technology in its factories. Packaging material is being reformulated for recyclability and reduced plastic usage. Each Mars bar, though it appears simple, is the product of a deeply engineered process, combining food chemistry, automated manufacturing, and strict quality assurance to ensure uniformity on a scale of millions of units per day. From raw cocoa mass to wrapped bar, the journey is a marvel of food industry precision. Snickers bars begin their life in a highly coordinated manufacturing facility where precision equipment, food science, and industrial engineering merge to produce one of the world's most popular candy bars. The process starts at the very foundation, the peanuts. Whole, raw peanuts arrive at the factory in food-grade bulk containers or via pneumatic tankers. These nuts are funneled into intake hoppers equipped with vibrating screens and magnets to remove stones, shells, or metal fragments. From there, they're transferred to silos with humidity and temperature controls, where they await roasting. The roasting process is crucial in developing the Snickers bar's signature crunch and roasted aroma. The peanuts are moved from silos into rotary drum roasters, which tumble them continuously at temperatures between 160 to 180 degrees Celsius. The roasting cycle is tightly timed, usually around 20 to 25 minutes, and computer systems monitor kernel temperature, moisture release, and color development using near-infrared sensors. Once roasting is complete, the peanuts are transferred to a cooling conveyor where chilled, filtered air rapidly reduces the kernel temperature, halting the cooking process and preserving the ideal crunch. After cooling, the peanuts are split into two processing streams. A portion is designated for whole peanut inclusion. These go through size grading systems and optical sorters that scan for broken or discolored nuts. Defective peanuts are automatically removed with precise puffs of air. The selected whole peanuts are sent to temporary storage hoppers until they are needed at the assembly stage. The other stream is milled into granulated peanut fragments. The peanuts pass through precision grinders that can be adjusted to produce different textures, from coarse granules to fine peanut meal. These different textures are essential as the coarse fragments are used in the caramel mixture for crunch, while the finer ones enhance the nutty flavor in the nougat. While the peanuts are being processed, the nougat, a critical layer in every Snickers bar, is produced in an adjacent line. The nougat base is made by mixing glucose syrup, sugar, powdered milk, and a whipped protein sauce, typically egg whites or hydrolyzed soy protein, isolate. These ingredients are heated in a batch cooker where sugar and glucose syrup dissolve and are cooked to a specific temperature to ensure the right consistency. The hot syrup is pumped into an aeration chamber where it's rapidly whipped to incorporate microbubbles of air, turning the dense syrup into a light, chewy base. To this base, ground peanut meal and sometimes cocoa powder are added, depending on the variation of Snickers being produced. The aerated nougat mixture is deposited onto a moving steel conveyor belt in a uniform slab, usually about 10 to 15 millimeters thick. The slab is leveled with motorized spreaders to ensure consistency in thickness, and then it enters a cooling tunnel. The tunnel gradually brings down the temperature of the nougat slab using fans and chilled air, solidifying the structure just enough for it to carry additional layers without collapsing. The next step is caramel preparation. Caramel for Snickers is not a generic mixture. It's custom designed for the brand's chewy, stretchy mouthfeel. It begins with a combination of glucose syrup, sugar, milk solids, and butter, cooked under vacuum to reduce the boiling point and develop flavor while maintaining softness. This caramel is cooked in large, continuous cookers that can process hundreds of liters per hour. The caramel is cooled slightly and mixed with coarse ground peanuts, creating the crunchy, rich upper layer of the bar. This hot caramel peanut mixture is deposited directly onto the cooled nougat slab. The deposition system includes a manifold that spreads the mixture evenly across the slab, forming a second layer. This dual-layered slab continues down the production line into another cooling tunnel, where the caramel firms up without hardening completely, remaining flexible for cutting. Once sufficiently cooled, the dual-layer slab is transported to the guillotine cutter. Using ultrasonic or hot wire blades, the slab is cut into bar-width strips and then into individual bar lengths, usually 50 to 60 grams each. These bars are then conveyed into the enrobing line, where they receive their final layer, chocolate. The chocolate coating used on Snickers bars is made in-house, using a proprietary blend of cocoa mass, cocoa butter, sugar, and milk powders. These ingredients are refined and conched in large machines that heat, mix, and aerate the chocolate to develop flavor and reduce particle size. The finished chocolate is held in jacketed tanks at a precisely controlled temperature of 30 to 32 degrees Celsius, ready for tempering. Tempering involves carefully controlling the crystallization of cocoa butter to ensure that the final chocolate has the right snap, gloss, and shelf stability. The tempered chocolate is pumped into enrobing machines, long tunnels, where a curtain of liquid chocolate coats the bars as they move along a mesh conveyor. A bottoming wheel applies chocolate to the underside of each bar, ensuring full coverage. Excess chocolate is removed using air knives, and the bars are passed under vibrating plates to level the coating. The coated bars are conveyed into a cooling tunnel approximately 20 to 30 meters long. The temperature in the tunnel drops from room temperature to about 8 to 10 degrees Celsius in graduated steps. This controlled cooling sets the chocolate without causing bloom or shrinkage. By the time the bars emerge, they are fully formed and ready for packaging. Each Snickers bar is picked up by robotic arms and placed into horizontal flow wrapping machines. Printed packaging film is formed around the bar, sealed at both ends and along the back using heat sealing jaws. The sealed bars are printed with a batch number, expiry date, and traceability code. Optical scanners inspect each package for proper seal integrity, print clarity, and alignment. The wrapped bars are grouped into cartons using high-speed collation systems. Depending on the SKU, bars may be packed into boxes of 12, 24, or 48 units. The cartons are sealed, labeled with logistics and traceability data, and palletized by robotic stacking systems. Pallets are shrink-wrapped and moved to staging areas for shipment. Throughout this entire process, quality assurance plays a vital role. Inline sensors and cameras continuously monitor chocolate viscosity, nougat density, caramel flow rate, peanut distribution, and packaging integrity. Manual samples are taken hourly and cut open for cross-sectional inspection. Taste tests are conducted daily by trained sensory teams who evaluate aroma, flavor, mouthfeel, and visual quality. Products that fail any stage of inspection are diverted, documented, and analyzed to prevent recurrence. Snickers factories are designed with food safety and hygiene as top priorities. Staff wear full PPE, including hairnets, gloves, and smocks. Entry to production areas requires hand washing, sanitization, and often passing through air showers or floor sanitizers. All surfaces are made of food-grade stainless steel, and machinery is built with clean-in-place systems that allow automated washing and sanitization between batches. Environmental sustainability is another integral part of Snickers manufacturing. Mars, the parent company, implements energy-efficient roasting systems that recover heat, water reclamation systems that treat and reuse rinse water, and LED lighting to cut emissions. chocolate and nougat trimmings are collected and either reused in new batches or converted into animal feed, while packaging material waste is recycled or reused wherever possible. From the first roasted peanut to the moment the wrapper is sealed, the making of a Snickers bar involves over a dozen steps, hundreds of parameters, and thousands of quality checks. Every component, from the protein foam in the nougat to the precise shear profile of the caramel, the fat crystal structure of the chocolate, and the crunch of the peanuts, has been engineered and tested to deliver a consistent, craveable bite. This integration of traditional confectionery with high-efficiency industrial production is what enables Snickers to be produced in the millions each day, while maintaining the same rich, multi-layered flavor and texture that has made it a global staple for decades. The manufacturing process for Ruffles potato chips begins long before a potato even enters the production facility. It starts with agricultural planning and controlled sourcing. Ruffles, as a brand under Frito-Lay, utilizes proprietary potato varieties that are cultivated specifically for chip production. These aren't the same types of potatoes used for baking or mashing. Instead, Frito-Lay contracts with dozens of partner farms across the United States and other regions to grow chipping potatoes, varieties like Atlantic, Snowden, or proprietary Frito-Lay hybrids that are selected for their specific characteristics: high dry matter content, low sugar levels, uniform shape, and dense texture. Each crop is grown with tight controls on irrigation, fertilizer use, and harvesting schedules to ensure consistency and minimize storage degradation. Potatoes that are too moist, sugary, or irregular in shape would result in chips that are oily, dark, or fragile, none of which meet the Ruffles brand standard. At harvest, potatoes are collected using automated harvesters equipped with rubber conveyors that minimize bruising. They're loaded into transport trucks and sent to the factory, often within a few days of being pulled from the ground. When the potatoes arrive at the processing plant, they enter the facility through the raw receiving bay. These are enclosed intake areas where truckloads are weighed, logged, and tested before being accepted for processing. At this point, technicians from the quality assurance team extract random samples from the load to check for size uniformity, sugar content, starch levels, and moisture content. Any batch of potatoes that falls outside the tight specification window may be rejected or diverted to other non-chip product lines. Once cleared, the potatoes are offloaded from the trucks into a large receiving pit, essentially a hopper connected to a series of conveyor belts. From here, the potatoes are moved toward the initial cleaning phase. This begins with the destoning drum. As the potatoes enter this large rotating cylinder, jets of water and the rotating action cause heavier materials, like rocks or clumps of soil, to separate and fall through grated bottoms. Potatoes are lighter and are lifted to the next stage. From the destoning drum, the potatoes enter the pre-wash flume system. A flume is a water-filled channel that moves product gently using the flow of water instead of belts. This minimizes physical damage to the raw potatoes while removing dirt and loose debris. The flume water is treated and recirculated through industrial filters and chemical dosing systems to ensure both sanitation and water conservation. In many modern plants, the water used in these systems is part of a closed-loop recovery system designed to reduce environmental impact. The next stop is the rotary scrubber. This is a long, cylindrical machine fitted with internal brushes that rotate as the potatoes pass through. High-pressure nozzles spray water as the tub rotates, scrubbing away any remaining mud, sand, or biological debris. The inside of the scrubber is lined with abrasive surfaces that help clean the rough skin of the potato without cutting into the flesh. The goal here is to deliver a clean, undamaged potato with its skin still intact, ready for inspection. After scrubbing, the potatoes are lifted out of the washer by a cleated incline conveyor and passed through a visual and automated inspection system. In this phase, both human inspectors and camera-based vision systems work in parallel. The conveyor belt is engineered to spread out potatoes into a single layer, and each tuber moves past a combination of high-resolution cameras and infrared sensors. These systems are trained to detect green spots, bruises, cuts, or signs of rot. Any substandard potatoes are ejected via automated diverter arms or air jets, which remove the faulty items from the belt and send them to waste or compost streams. Human operators stationed along the line also remove visibly defective items that machines might miss, such as those with odd shapes that won't slice well on the crinkle-cut blades. Every removed potato is scanned and logged into the factory's waste tracking system, allowing operators to identify trends and address upstream sourcing problems if too many rejects appear from a single truckload. Now that the potatoes have passed visual inspection, they move on to the peeling station. For Ruffles, peeling is essential. While some gourmet-style chips retain their skins, Ruffles chips require a smooth, peeled surface to produce clean, consistent ridges during slicing. Peeling is achieved using a combination of steam and abrasion in what's known as a steam peeler. The steam peeler is a high-pressure vessel that receives a batch of potatoes, seals the chamber, and subjects the potatoes to pressurized steam, usually around 180-220 psi for 8 to 20 seconds. This superheated environment rapidly loosens the outer skin layer by partially gelatinizing the pectin between the skin and the underlying tissue. Once the steam cycle ends, a sudden pressure drop causes the skin to puff and detach slightly from the flesh. Immediately after this, the potatoes are discharged into an abrasive roller peeler. This is a rotating drum lined with rough surfaces, often embedded with carborundum grit, that gently scrubs the now loosened skins away. Water sprays are used to flush away the skins and clean the exposed potato surface. The amount of skin removed is carefully monitored. Too much abrasion would remove usable flesh and increase waste. Too little would leave patches of skin that affect the slicing process. The peeled potatoes are rinsed again in chilled water to stop any residual thermal activity and prevent enzymatic browning. A small dose of food-safe antioxidant, like sodium metabisulfite or citric acid, may be added to the rinse water to preserve the pale color of the peeled surface and prevent discoloration before slicing. At this stage, the potatoes are fully clean, peeled, and ready for their signature transformation, being cut into the iconic ridged slices that define a Ruffles chip. With the freshly peeled and rinsed potatoes now ready for transformation, the next phase in the Ruffles production process focuses on slicing, the moment where whole tubers are precisely cut into their distinctive ridged form. The ridges are far more than a visual or marketing detail. They play a critical role in the chip's strength, texture, and frying performance. This stage involves advanced slicing technology, careful temperature and starch control, and continuous monitoring to ensure each slice is the exact thickness, shape, and structural consistency required for optimal cooking and crispness. The peeled potatoes are transported to the slicing area via gentle, water-based flumes or soft conveyor belts to minimize impact and prevent bruising. Once they reach the slicing units, the potatoes are fed one by one into high-speed rotary slicers designed specifically for crinkle or corrugated cuts. These industrial slicing machines use a rotating impeller or feed wheel to press each potato firmly against a stationary, razor-sharp cutting head fitted with ridged blades. The blades are precisely machined to form a consistent wave pattern, typically with a wave amplitude of 1.5, 2.5 mm and a thickness of around 1.3, 1.5 mm. Unlike flat chip slicing, where a smooth blade is sufficient, Ruffles require a carefully engineered ridged blade made of hardened stainless steel. These blades are aligned at specific angles to produce even, undistorted waves along the chip's entire surface. The sharpness, speed of rotation, and pressure exerted must be perfectly balanced. Too much force or misalignment can result in chips with uneven ridges or broken tips, which would either fry unevenly or be rejected later during inspection. The sliced potatoes are ejected from the slicing drum at high velocity and collected in a shallow trough or on a belt that immediately begins the next critical step: starch removal and surface moisture control. Every potato contains natural starch, and when sliced, a large amount of that starch is released onto the cut surfaces. If not removed, this surface starch can interfere with the frying process, causing chips to stick together, fry unevenly, or develop burnt spots. It can also result in a greasy or gummy mouthfeel, which is unacceptable for Ruffles' clean, crisp texture. To remove excess starch, the slices pass through a multi-stage rinsing system. In the first phase, they enter a flume filled with cold, recirculated water, where they are gently agitated to dislodge free starch. The water in this flume is constantly filtered and monitored for starch content, with automated control systems adjusting flow rate and replacement intervals to maintain effectiveness. Following the first rinse, the slices often move through a series of cascading rinse curtains, sheets of filtered water that fall like waterfalls over the slices as they travel along a mesh or perforated conveyor belt. This helps remove residual starch without applying any mechanical force that could break the delicate ridges. After rinsing, the slices must be dried to a specific degree, not fully desiccated, but dry enough on the surface to allow the hot oil in the fryer to crisp the exterior without creating steam pockets or excessive foaming. This is achieved using a dewatering shaker and an air drying tunnel. The dewatering shaker is a vibrating belt or tray that shakes the slices gently to remove bulk water. The slices then pass under high-velocity air knives, rows of precisely aligned jets that blast room temperature or slightly warmed air across the chip surface. The air knives are tuned to create a shearing effect that strips away surface moisture while maintaining the shape and integrity of the ridged cuts. At this point, the slices are considered ready for frying, but only if they meet one final set of pre-cook inspection criteria. Before entering the fryer, the slices pass through an optical sorting system. This state-of-the-art inspection station uses a combination of high-resolution cameras, infrared sensors, and sometimes laser scanners to detect defects such as green spots, bruising, overly large slices, or broken pieces. Defective slices are rejected with microbursts of compressed air, which knock them off the main conveyor line and into waste or reprocessing bins. The acceptable slices, meanwhile, are evenly distributed across the width of the fryer in feed conveyor to ensure uniform exposure to hot oil. Frying is where the raw slices become what we recognize as potato chips. And for Ruffles, this step is both art and engineering. The chips are fried in continuous fryers, long stainless steel troughs filled with high-temperature cooking oil. The oil is typically a carefully formulated blend of vegetable oils, often including sunflower, corn, or canola oil, chosen for their high smoke points, neutral flavor, and oxidative stability. The oil is filtered, treated, and replaced on a tightly regulated schedule to maintain quality and avoid flavor degradation. As the slices enter the fryer, they are immediately submerged by a submersion conveyor that ensures they stay evenly beneath the oil's surface throughout the cooking process. The oil is maintained at a precise temperature, usually between 170 degrees Celsius and 190 degrees Celsius. This range is critical. Too cool, and the chips absorb oil and turn soggy. Too hot, and they brown too quickly or develop burnt notes. Each chip is cooked for approximately 2 to 3 minutes, depending on thickness, oil composition, and desired moisture content. Inside the fryer, the chips expand slightly and crisp as their internal water content rapidly evaporates. The ridged surface of Ruffles causes the chip to fry unevenly by design, creating micro variations in texture that result in a more substantial bite and greater structural integrity. The ridges also slow oil drainage, allowing a slightly longer dwell time that contributes to the chip's durability and resistance to breakage during dipping. The fryer is equipped with multiple sensors and flow meters that measure oil temperature, turnover rate, chip feed rate, and even in-oil moisture concentration. These data are analyzed in real time by the factory's central control system, allowing operators to make immediate adjustments. In many facilities, the frying process is linked to upstream slicing sensors. For example, if slightly thicker slices are detected coming from the cutter, the fryer conveyor speed is slowed accordingly to ensure proper cook time. As the chips emerge from the fryer, they pass through an oil draining phase. A vibrating conveyor with a perforated surface allows excess oil to drip off. This is immediately followed by an air cooling system that begins to lower the chip's temperature, halting further cooking and locking in texture. Cooling is essential not only for texture stability, but also to prepare the chips for seasoning, which happens shortly after. But before we get to seasoning, there's a critical interlude in the process: moisture analysis and inline quality control. At this stage, a small percentage of chips are diverted through a sampling chute to a nearby test station. Here, technicians use moisture analyzers, color meters, and even acoustic crispness testers to evaluate product characteristics. These tests ensure that the chips meet the factory's targets for final moisture content, color uniformity, and physical integrity. As the freshly fried and cooled Ruffles chips exit the fryer and pass through preliminary quality control, they enter one of the most dynamic and highly controlled stages in the factory: seasoning. This is the phase where the chips receive their final flavor identity, whether it's the original lightly salted variant, sour cream and onion, cheddar and sour cream, jalapeno ranch, or any of the other regional and seasonal flavor options Ruffles is known for. Applying these flavors evenly, consistently, and at high speed while preserving the chip's structural integrity and minimizing waste is a challenge that modern factories solve using specialized equipment and real-time process monitoring. The chips arrive at the seasoning station on a wide, inclined conveyor or vibratory tray that serves two main functions. It spreads the chips out into a single layer to prevent overlap, and it gently agglomerates chips to control their flow into the seasoning drum without damaging them. Due to the ridged shape and the thicker cut of Ruffles compared to standard potato chips, seasoning application must account for deeper surface area and variable orientation. Some chips will face ridge side up, some down, some angled. Seasoning application takes place inside a rotating tumbler drum, also called a flavor drum or seasoning cylinder. This stainless steel drum is set at a slight incline and constantly turns on its horizontal axis, gently lifting and tumbling the chips while they rotate through it. At the entrance to this drum, a continuous metered flow of seasoning powder is dispensed through an auger-based dosing system. The seasoning blend, pre-mixed according to a proprietary formula, includes a combination of salt, natural and artificial flavorings, cheese powders, dehydrated dairy, onion and garlic powders, spices, yeast extract, and anti-caking agents. The dosage rate of the seasoning is tightly controlled via real-time feedback systems. Optical sensors measure the chip volume entering the drum, and the dosing screw adjusts the delivery rate to maintain an ideal flavor to surface area ratio. Too much seasoning leads to clumping, over-salted chips, and waste. Too little results in bland or unevenly flavored chips that fail quality checks. For cheese-based seasonings, which are more moisture sensitive, the flow system may include a nitrogen-purged hopper or desiccant units to prevent clumping in humid environments. Inside the flavor drum, fine misting nozzles also spray a light coating of oil to help the seasoning adhere evenly to the chip surface. This atomized oil does not soak the chips, but rather creates a microfilm that holds the powder in place without compromising crunch. The rate of oil application, angle of spray, and temperature are all adjusted based on the type of seasoning used. For example, heavily coated varieties like cheddar and sour cream require more binder oil and a slightly longer tumbling duration to ensure every chip is fully and evenly coated. Throughout the seasoning process, line operators and quality assurance technicians take random samples every few minutes. These samples are assessed for seasoning coverage, color intensity, and surface powder levels. In more advanced factories, seasoning uniformity is checked with hyperspectral cameras that scan the chips as they exit the drum, detecting variations invisible to the human eye and triggering alerts or auto-calibration if inconsistencies are detected. Once the chips have been properly seasoned, they are transferred to the packaging phase. This is a highly automated and synchronized system that must meet several objectives simultaneously. Protect the chips from breakage, preserve freshness, prevent contamination, provide product information to the consumer, and maintain traceability for safety audits. Packaging begins with product accumulation. Conveyors from multiple seasoning drums may feed into a single accumulation hopper or weigher, depending on line configuration. This hopper temporarily holds chips before they're dispensed into individual bags via a multi-head combination weigher. A multi-head weigher is an advanced piece of equipment with multiple radial feed hoppers arranged in a circular pattern. Each hopper releases a small portion of chips, and a central computer instantly calculates which combination of hoppers adds up closest to the target weight, say 28.3 grams for a single serve bag. This combination is released simultaneously into a timing hopper, which drops the exact weight into a vertical form-fill-seal packaging machine. The VFFS machine forms bags from a continuous roll of printed plastic film, often made from multi-layer laminate materials with barriers against oxygen, light, and moisture. As the chips drop from the weigher into the forming tube, the film is pulled around the tube, sealed lengthwise, and sealed again at the top and bottom with heated jaws, creating a pillow-style bag. Before the top seal is made, a precise dose of nitrogen gas is injected into the bag, a process known as nitrogen flushing. This replaces the oxygen-rich air inside the package to reduce oxidation, extend shelf life, and protect the chips from crushing by slightly inflating the bag. Once sealed, each bag moves through a print station where batch codes, production time, plant ID, and expiration dates are applied using inkjet or thermal printers. Bags then pass through check weighers to confirm accuracy. Any bag outside the designated weight window is automatically rejected and diverted to a rework bin. Metal detectors or X-ray systems scan every bag to ensure no foreign objects have entered the product during processing. This is standard for all snack food production and a critical part of food safety compliance. From there, the sealed and verified bags are grouped into cartons or display trays by robotic case packers. These cartons are sealed with tape or glue and labeled with barcodes and tracking information. Finally, cartons are stacked onto pallets by robotic palletizers, often using suction cup grippers or clamp arms to gently stack without damaging contents. Pallets are wrapped in stretch film and staged in the finished goods warehouse, which is climate controlled to preserve chip texture and flavor. At every point along this packaging line, sensors, programmable logic controllers, and SCADA systems monitor performance metrics, line speed, reject rates, weigher accuracy, sealing temperature, film feed rate, and more. Maintenance logs and process trends are analyzed weekly to identify emerging issues, improve throughput, and reduce product loss. Beyond the physical movement of chips, there are strict sanitation and allergen management systems in place. Since some Ruffles flavors may contain milk, cheese, or other allergens, production lines must be deep cleaned between flavor runs. Clean in place protocols involve dismantling sections of the line using high-pressure washdowns, food-safe detergents, and microbial swab testing. Detailed records of every cleaning cycle are logged and audited regularly. In addition to cleaning, factories must manage cross-contamination risk during flavor changeovers. This includes running purge batches, segregating flavoring agents in separate storage silos, and using dedicated feed lines wherever possible. Every batch of Ruffles is linked back to a full traceability profile, covering raw material lot codes, equipment used, line operator IDs, and environmental conditions during processing. As the freshly packaged Ruffles chips leave the main production floor, the final phase of manufacturing comes into focus. A sophisticated web of logistics, sustainability efforts, continuous process optimization, and digital innovation. While the chips themselves are complete, the factory does not pause. Instead, a parallel system of data analysis, quality assurance, and supply chain orchestration continues operating in the background, ensuring the product not only meets current demand, but evolves to meet future expectations. These behind-the-scenes processes are integral to the long-term efficiency, environmental responsibility, and market success of Ruffles. At the heart of these operations is a factory-wide data infrastructure that tracks every input and output, from raw potatoes to finished pallets. Each batch of Ruffles produced is logged into an integrated manufacturing execution system. This software records the origin of each ingredient, the time and conditions of each processing step, the performance of every machine along the line, and even environmental metrics like room humidity and oil turnover frequency. The MES integrates with enterprise resource planning systems, providing real-time visibility into inventory levels, sales forecasts, and raw material consumption. This data is not merely archived, it's analyzed continuously using advanced analytics platforms and AI-based algorithms. These systems look for patterns in machine downtime, chip reject rates, oil consumption per batch, or seasonal fluctuations in potato solids. If a fryer begins to show a subtle increase in oil absorption, or if seasoning coverage becomes slightly more variable, the system flags it. Maintenance crews and process engineers receive alerts and can intervene before the issue affects product quality or efficiency. Predictive maintenance models also help avoid equipment failure by identifying when motors, pumps, or slicers are approaching wear thresholds. One of the key areas of focus in modern Ruffles factories is oil management. Frying oil is both a major cost and a major variable in product consistency and sustainability. The oil in the continuous fryer is constantly recirculated through filtration units that remove chip fines and particulates. Inline sensors monitor the free fatty acid content, color, and total polar materials in the oil, 3 indicators of oil degradation. When these metrics exceed defined limits, the system initiates partial or full oil replacement protocols. Some facilities have implemented smart fryer systems that dynamically adjust oil flow and heat profiles based on chip load and moisture level, significantly reducing oil turnover without compromising flavor or texture. Environmental sustainability is another priority embedded into Ruffles manufacturing. Frito-Lay, the parent brand, has committed to reducing water, energy, and greenhouse gas emissions across its snack food plants. One way this is achieved is through water reclamation. The flume water used to transport, wash, and rinse potatoes is filtered, UV treated, and reused multiple times before final disposal. Similarly, the steam peelers are equipped with condensate recovery systems that recycle steam condensate back into the boiler system, conserving energy and reducing water use. Electricity usage is optimized through variable frequency drives on conveyors and pumps, while LED lighting, motion sensors, and insulated cooling tunnels help minimize unnecessary energy waste. Some Ruffles production plants are now partially powered by renewable sources, including solar panels and biogas captured from on-site food waste digesters. Waste heat from fryers is recovered using heat exchangers and used to preheat incoming wash water, further boosting energy efficiency. Waste management is another crucial part of the factory's operations. Trimmings from biscuit cuts, chips rejected for size or overcooking, and seasoning overage are all collected, logged, and sent to animal feed processors or converted into biofuel when food safety protocols allow. Even the excess oil removed during de-oiling phases is collected, filtered, and sold to biodiesel manufacturers. Packaging materials are optimized for minimal plastic use, and packaging engineers continuously evaluate new laminates that offer better barrier performance with reduced environmental impact. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated. Five Guys moves thousands of pounds of beef and buns through a supply chain so intense it runs like a high-speed burger machine. Behind every fresh, made-to-order meal is a massive factory system designed to deliver consistent flavor with zero shortcuts. In this documentary, we go inside the operation powering one of America's most iconic burger chains, from raw ingredients to grill-ready perfection. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated, but the buns are loaded in temperature-controlled staging areas and packed in sealed corrugated boxes to maintain freshness during transit. Any deviation in delivery, timing, or packaging temperature triggers a rejection at the restaurant level. In-store, the buns are stored at room temperature in designated bread racks, often rotated using FIFO principles. Staff members are trained to inspect buns visually and by touch. Any signs of excess firmness, moisture, or spotting lead to immediate disposal. Each bun is hand-prepared on-site, toasted on a grill with a light coating of melted butter before it becomes the vehicle for the burger build. This final touch, though simple, is only possible because of the structural integrity and texture delivered by the bakery's industrial process. Now that the core components of a Five Guys burger are accounted for, the beef, the fries, and the buns, it's time to examine the supporting elements that complete the burger experience: bacon, cheese, toppings, and condiments. These items may seem simple, but each is chosen and prepared with deliberate intent, and, in most cases, centralized at an industrial level before being delivered to restaurants. Starting with bacon, Five Guys sources thick-cut, naturally smoked strips from approved pork processors in the US. The bacon is not fully cooked at the factory. Instead, it's partially cooked or pre-rendered to about 60 to 70% doneness, then chilled and vacuum packed in clear plastic pouches. These pouches are labeled and sorted by weight and count per case, with each case tagged for traceability. The bacon is cooked to completion in the restaurant, where staff lay it flat on the grill and crisp it to order. This two-step process, initial industrial cooking followed by final preparation, ensures food safety, flavor development, and grease reduction